Suman and Dinesh, it's 2:10. Should we waiting for another 5 minutes or should we start for the people who have come on time?
We'll wait for like. Sir, we'll wait for another maybe 2 minutes.
Yeah, fair enough. No, but at 2:15 maybe.
Yeah, do
We'll
it,
wait
sir.
for
Yeah,
5 minutes.
fine. Yeah,
2:15 we
We
can
wait
start.
for
Yeah.
5 minutes, sir, and then we'll
yeah,
start.
right.
Yes.
Yeah.
Thank you. Hello, Suman and Dinesh.
Yes, sir. Good to go.
Yeah, good to go. No worries. Suman, I will be able to do the in case if that's
Okay, sir. Yeah, we can start.
yes.
Suman, shall I start with the introduction of the speaker?
Yes, sir.
Okay, thank you. Hello, everyone. Very good afternoon. Welcome for the today PDP series, AEROTHON 25 Tech series on the topic structural analysis of drones with Ansys Mechanical. Today we have with us the speaker, Mr. Shyam Kumar Manikonta, application engineer, CAT from India. So, a small bio of him. Mr. M. Shyam Kumar holds a master's degree in structure and design and have over 5 years of experience in teaching, research, and industry applications. Currently, he is an application engineer at CAT from India. He specializes in structural simulation, finite element analysis, and numerical methods, with extensive expertise in Ansys Mechanical as well as LS Dyna. He works on solving complex engineering challenges, optimizing structure designs, and enhancing simulation workflows across various industries, including aerospace, automotive, and heavy engineering. His core competencies include linear and nonlinear structure analysis, impact and crash simulation, as well as dynamic response analysis. Welcome, Mr. Shyam Kumar, sir. Over to you.
Shyam, you may share your slide deck.
Yeah, hope my voice is loud.
Yes,
Yes,
it's
sir.
audible. Yes.
Yeah, perfect. Yeah, thank you, Dinesh, and thank you, Venkat. Quickly, I'll share my screen. Yeah, hope my screen is visible too.
Yes, sir.
Yes.
Yeah. Yeah. Welcome to the present session, structural analysis of drone using Ansys Mechanical. And myself, Shyam Kumar Manikonda, and I'm an application engineer. I generally deal with the structural application and relevant simulations. And coming to the present agenda, I hope you have seen this agenda in our flyer. So we will start introducing about simulation and virtual development of the simulation, and we'll show you the drone system overview, and immediately we'll start about the numerical method, the FEM finite element method, and various element formulations, what we can use in FEM method, which is a numerical method. And we'll show you the workflow, particularly Ansys mechanical, and using the mechanical using a workbench. We will show you how we can set up the simulation step by step through a workflow, and we'll show you what are the different structured analysis we can have, and what are the relevant tools we can use for conducting such structural analysis. And we will give you two demonstrations. One is a static structural analysis and another is a model analysis. Okay, so both the analysis will be performed on a model helicopter or maybe the hexacopter. And at the end, I'll show you the best practices and followed by a discussion queries from your side. So let's see what motivates us going for a simulation. We will see. First of all, what is a simulation? Simulation means most of you might be knowing about the meaning itself. So it's
Hello?
replicating. Yes, hello.
हाँ बोल ना वो मीटिंग मध्येच आहे
Teams, kindly mute yourself.
Thank you.
Yeah, I've muted all the
Simulation.
attendees. Shyam, go ahead, please.
Yeah, perfect. Yeah, simulation, the word we will see, simulation means it's replicating the physical phenomena in your virtual world. So whatever the problem you may see in your real world scenarios, so those kind of problems we can virtually replicate using some environment. So that process we say it's a simulation, and we'll use some particular computerized tool for setting the virtual environment. Okay, so if you see prototyping, generally prototyping, the word associated with the two types, so physical prototyping and virtual prototyping. So what we do in simulation means we will identify a physical prototype and we will replicate the physical prototype into virtual prototype. Okay, so on that virtual prototype, we will do the testing and analysis side of it. Okay, let's say there is a classic example you could see in the right side. So that's a transmission box, particular gearbox if you see. So generally it will take around 6 weeks for manufacturing the particular physical prototype. So if you stick with the physical prototyping along with the physical prototyping, if you stick with virtual prototyping, so it will help you reducing of your particular production time. You can reduce it by 1 to 2 weeks. Okay, so without simulation, if you are not adopting simulation, generally it may take 6 weeks of production time. But if you use the simulation, if you use it, then the production time can be reduced, drastically, like 1/4 of the time you can reduce the production time. Okay, there are many tools need to be manufactured. Okay, so for the prototype, physical prototype construction and production. Okay, so let's say if your physical prototype fails, then what happens? So you have to start you have to design everything. So modifications you have to include. Okay, so manufacturing methodology we need to change. Okay, so all those things you have to do multiple iterations if your particular physical prototyping is fails. Okay, so all those kind of scenarios you could simulate using the virtual environment by means of some particular simulation tool. Okay, so what simulation will help you? So while doing your production or prototyping, so if you utilize the simulation, it will help you a lot. So we generally say it's a pervasive simulation. So Ansys helps you developing this pervasive simulation. So what means simulation can be applied in any stage of your production cycle. So if you see the first figure, the circular figure, so it tells you so during your entire production cycle time, you can use simulation in any stage of it. So that's why we say it's a pervasive simulation. So and you can see the simulation impacts there. So the line items, if you see, it will help you rapid innovation. It will reduce your manufacturing cycle times, and uneven risks can be reduced. Okay, so then again, quality of your production can be increased, and variety of complex parts you can manage. Okay, then again, ultimately you will improve your revenue, and you can save money costs incurred in it. Okay, so these are the basic things you can understand. So this is what the classic example. So there is a company, AGCO Fent. So what they claimed, using the simulation, particularly Ansys simulation, they have claimed their prototyping time got reduced from 8 weeks to 1 or 2 weeks. So this is a classic example you could see. And this is another design. So this is a totally new design, air multiplier from Dyson. Okay, so it's a new design of table fan. So you can say that's a bladeless fan. So what it does, it pulls air into the ring and amplifies it by further 15 times. So airflow can be improved, like strong and smooth airflow can be given. So it's an expensive thing because it's a new design and there is no background before this particular new design. So what I'm saying from this slide, so any kind of a new design also you can develop using your simulation thing. So you don't need a history of the existence of that particular part. So you can start doing your product very innovatively without having any previous existence of that particular model. So let's say you have a virtual development process. So generally it will be having some 3 stages. So we will start with the drafting of that particular design or model. And once you done the model, you have to do the validation. I means you need to check whether it is functioning properly or not virtually initially, because it's a virtual development process we are telling about. So all the things will be done virtually using your simulation platform, particularly Ansys. Okay, so drafting and validation. At the end, you can do the integration also. Ansys is providing option of integrating your virtual model, using your real world data. Okay, so, and these are the tools in your virtual development process. So if you correlate this previous slide and this slide, so drafting, validation, integration. So drafting, we have Ansys Discovery. It's a new tool. So for designing or modeling, so we have the tool Ansys Discovery. Okay, so not only Ansys Discovery, we have other tools also. Space Claim is another thing, and Design Modeler is another thing. So we have 3 different tools for drafting your model. And coming to the solver or validation purpose, so we will use validation purpose. Different tools are there based on the physics. So structural physics, electromagnetics physics. Okay, then again fluid physics. All those physics relevant tools we are having. So Ansys is offering solver tools based on the physics of what you are dealing with. Okay, that is for the validation view, and we have the tools for the validation. And coming to the twin builder, so this is a twin builder which will be used for integration of your virtual prototype by means of real world sensor data. Now coming to portfolio. So earlier what I showed you, these are the basic things generally any person can use based on their physics. Okay, so these are the basic things like drafting, validation, and integration. Okay, if you see the portfolio of Ansys, so Ansys is offering a biggest portfolio than any other industry available software. So you could see based on your physics, different tools are there. And particularly, I am not going to spend time. I'm not spending much time on this particular portfolio because based on the present session, I have to stick with the structures portfolio. Okay, so in this structures portfolio, if you see, starting with mechanical, elastina, forming, so like 8 different tools are there in structures, and that too we are going to stick with a single tool, that is mechanical. So you can understand how big GANS is internally. Okay, so based on the structure, based on the physics, what you are sticking with, so you have to identify which relevant tool you have to work. Okay, as I told you, we will be sticking with the mechanical based on the present session. Okay, so Ansys structures portfolio, if you see, 8 different tools are there, starting with mechanical. So mechanical is the tool one could do all the implicit structural mechanics problems. So implicit means, so hopefully you might be knowing implicit simulation means implicit analysis means analysis or problem duration will be longer, like static problems, dynamic problems, creep problems. So all these kind of problems we will say it's a implicit simulation, implicit analysis. Okay, so all such problems, so we could utilize Ansys mechanical performing that implicit structural mechanics problems. So just remember, so the first one is mechanical, that is a tool used for doing the implicit structural simulations. Examples will be statics, dynamics, and creep problems. Okay, then coming to LS-DYNA, so mechanical is for implicit problems, then conversely, LS-DYNA will be for the explicit simulation problems. So explicit simulation problem means, if time duration, if I tell you, so the time duration will be of a milliseconds. That means short duration problems. Okay, so mechanical is for long duration problem solver, and LS-DYNA is used for simulating the short duration phenomena. Like short duration phenomena means drop problems, impact problems, crash simulations, penetrations. Okay, so all those kind of problems, the time duration will be very smaller. So it takes like milliseconds. Okay, so millisecond duration. So small duration problems. So a mechanical is for implicit simulation, implicit problems, structural mechanics problems, and LS-DYNA is for explicit structural mechanics problems. Okay, then coming to the motion. So hopefully motion means you can understand this excavator. So it is a combination of so many parts interconnected together. So each part we can say member. So all the members are connected, and such thing we generally say is a mechanism or machine. Okay, so those kind of mechanisms and machines we can have the kinematic studies. Okay, so those kind of studies we could perform using this motion tool. Okay, then again coming to forming tool is for manufacturing applications, particularly sheet metal and stamping applications. All those manufacturing problems or such problems we can simulate using the forming tool. Then Sherlock is a mixed tool, mechanical as well as electronics. So it's a Sherlock is a tool for electronics reliability, particularly when it is subjected to implicit load cases or explicit load cases. Okay, so using the mechanical and Elestina data, it will integrate the data from mechanical and Elestina tools to Sherlock. Okay, so those kind of loads will be on a electronics parts, particularly PCBs. Okay, so those kind of PCBs subjected to implicit and explicit load cases, so we can use Sherlock for calculating the electronics reliability. Then again, additive solutions. Additive solutions means hopefully everybody knows about additive solutions, right? Additive manufacturing. So that is a trending thing. Okay, so it deals the entire additive manufacturing workflow. It covers everything from design for manufacturing, design for additive manufacturing, DFAM concepts throughout through validation, print design, process simulation, and exploration of materials. Okay, so all those things can be done using the additive solutions. Then again, encode design life. There is another tool, so which is used to know the fatigue failure or fatigue life of a particular product or the assembly. Okay, so fatigue life prediction tool, particularly this encode design life. Okay, then again Autodyne. So Autodyne is again like LS-DYNA, the same kind of things can be done using Autodyne. Okay, but Autodyne these days it is kept in maintenance mode because whatever the capabilities Autodyne can do, the same thing can be done using LS-DYNA also. Okay, so what I'm saying, Autodyne is generally used for the particularly short duration severe loading cases. Okay, short duration severe loading cases like high velocity impacts, explosions, and ballistic simulations. Okay, so the Autodyne is specialized in this particular short duration severe loading cases. Okay, but after after acquiring this LS-DYNA, so whatever the capabilities Autodyne is capable, so those cases can be done using LS-DYNA also. So that's why Autodyne is kept in maintenance mode. So we can say from this slide, you should remember about mechanical and LS-DYNA. So mechanical is for long duration problem simulator, and LS-DYNA is for the short duration problem simulator. Now before going to talk about our workflow, let's see the system overview. Okay, so let's say we have some quadcopter. Okay, so these are the different typical different systems you can understand from the image. So starting with battery, GPS module, flight controller, motors, antennas, propellers, payloads. Okay, so the particular aim is to have the payload taken in your space in your environment. So, but why I'm showing this, because this is an overview of your system of your quadcopter, but we will be sticking to a different aspect here. So there are different engineering challenges you can have while designing a particular drone or unmanned UAV, unmanned aerial vehicle. Okay, so let's see this engineering challenges. Different engineering challenges will be there based on the physics. Okay, so with respect to body, with respect to reliability, semiconductor, sensors, functional safety and reliability. Okay, so we'll be focusing on this engineering challenges with respect to the structural integrity. So we'll be using our structures. You can have the structure made of the different composites. We could do the aerodynamic studies on that particular structure. But anyway, I'm not going to focus on this aerodynamic study and noise this time. A different session will be there on the aerodynamics of this particular structure. Again, so again, before going to our main demonstration, we need to have some a few things on finite element method. So finite element method is nothing but it's a numerical method which is used to solve your particular problem. Okay, so any problem, if you take engineering problem, okay, there are two ways of solving generally. So one is the on paper solution, that means analytical method. Using some equations, solution methodologies, you can perform that on a paper. But there will be many engineering problems, so you can't solve it on a paper. Okay, so those kind of problems we have to use numerical methods, and finite element method is one of such numerical method. As I told you, there are two ways of problem solving: analytical method and numerical method. Analytical method means hopefully every student might know about these analytical methods. Okay, on paper solutions we can have, and mostly whatever the analytical solutions you are having, those things are treated as exact solutions, accurate solutions. And using numerical methods, so we may or may not validate with respect to the analysis, analytical results what you have. So in FEM, what happens in FEM? FEM is, it's a numerical method. Let me highlight my pointer. So it's a numerical method which is used to solve the particularly complex engineering problems. So simple engineering problem, not the simple engineering problems, complex engineering problems, we will utilize the numerical method for solving. Okay, so generally, what is this complexity? The complexity means it will be associated with respect to the geometry, loading, and boundary conditions. Okay, so that is the meaning of the complexity of your particular engineering problem. Then in finite element method, what we do, we will take the entire domain, we will split the entire domain into small pieces, and those pieces will be of a finite shape and a countable number. Okay, let's say we have some, let's consider a flywheel. So flywheel, if you see, the flywheel, if we consider that as a domain, so what we will do in finite element method, we will split the entire geometry into small pieces as shown in the figure. So each piece we say it as an element, and each piece will be treated as a element. So each element will be surrounded by the corner points. So those points we say it as nodes. So what I'm saying, in finite element method, the main point is the entire domain under our observation will be split into small pieces. Each piece will be called as an element, and each element will be surrounded by the nodes. Okay, so from the figure, what you can remember, in finite element method, we will have different elements, and different elements will be there, and each element will be having the corner nodes. Okay, now let's see when we will utilize the, I told you already, when we will utilize the finite element method or the numerical method, whenever your problem is complex. Okay, so then only we have to stick with the numerical method, that is finite element method. Okay, that is what this slide is showing, saying. So let's say if you have a simple cantilever beam, okay, we know it is not a complex thing, it's a simple cantilever beam. So to calculate the deflection of the cantilever beam subjected to end load, okay, we don't need to go for simulation or computer to solve the problem, because it's a simple problem. So we have analytical result: deflection of the cantilever beam subjected to free end load. So we have this FL cube by 3EI. Okay, so to calculate the deflection, we don't need to use the simulation tool, because the geometry is simple. There is no complexity in your problem. Okay, so directly you can utilize this formula. Whereas if your geometry is complex, like, this is the cantilever beam, this is a regular cantilever beam, but this one is not a regular cantilever beam. Okay, it's an angled beam, and there is a wedge attached in between. Okay, so this is a little complex, complexity is there in this particular problem. So for solving the deflection of the image shown here, we definitely need to utilize the numerical method, that is the finite element method. Okay, so in finite element method, what it will do, it will have some three basic equations similar to the solution of a solution based on analytical method. Even the numerical method also, it will follow the three equations. So it will follow the equilibrium equations. It will be based on kinematics and material law. That means there will be some relation between strain and displacements and stress and strains. Okay, so these are the three equations I'm telling in the previous slide. So equilibrium equations it has to follow. kinematics, nothing but strain and displacement relation, and material law, stress and strain relation. Okay, so in finite element method, earlier what we remember, it is we will be having so many elements, and each element will be surrounded by the nodes. Excuse me. So in this slide, the highlighted red color highlighted formula, this is important thing. So how we are achieving this equation, we need to know. So from the this slide, it is based on a particular problem where it will show you how the equation can be developed from the classical analytical solution. So when a bar subjected to force F, we know the elongation formula. Okay, elongation is FL by EA. After rearranging a few terms, that means keeping force on one side and remaining things if you adjust on the other side, you will be getting in this form. And from this EA by L, I can make it as K. Okay, so this K multiplied by displacement is equated to force. Okay, so you need to remember this equation. This is a finite element equation. So where K is the EA by L, so K is called as the stiffness, and stiffness is depending on Young's modulus, area, and length. So that means material property and geometric property. So stiffness will be based on the material properties and geometric properties. So stiffness multiplied by displacement equal to force. So this is my equation. We call it as a finite element equation for a single element. Okay, so finite element method will be having elements and nodes, and each element will be having a equation, finite element equation, that is shown in the form k into u equal to f. Okay. If you open any textbook or based on finite element method, you'll be having different steps shown in the left side of the image. So different steps are there. But whereas in FEA, finite element analysis, it is nothing but finite element analysis is nothing but the integration of this method in your coding. Okay, we say it as a finite element method. So in finite element, in finite element analysis, there will be a coded form of the finite element method. Okay, so in FEA, we generally have three types of steps only. So one is pre-processing. That means you have to create the entire problem, and post-processing or nothing but the solution step. Okay, then post-processing. Okay, so in pre-processing, what we will do, we will establish the problem, we will create the problem. That means we will draw the geometry, we will develop we will develop the meshing. So meshing means splitting the entire geometry into small pieces. That is a main thing in finite element method. Okay, so we will establish the problem. That means draw the object, divide the geometry, and boundary conditions application. So all those things we say it as a pre-processing. And in the solution step, we will just identify the appropriate solution stage we will select, and we will solve it. Then once the solution is done, we will identify what are the results required. So that we say it as a post-processing. So pre-processing, solution, and post-processing. So these are the three categories in finite element analysis. And coming to the elements, so I just mentioned you about the element. So a problem domain can be split into small pieces. Each piece will be called as an element. Okay, based on your geometry of your domain. That means whether it is 1D, 2D, or 3D domain. Okay, so we will be having different type of element terminologies. If your geometry is 1D, accordingly you can have two-noded beam element and three-noded beam element. Okay, so you can see the horizontal description. So linear elements will be having the corner nodes, whereas quadratic elements will have intermediate nodes along with the corner nodes. Okay, that is the basic difference between linearity and quadratic elements. So linear elements means only end nodes will be there. Quadratic means along with the end nodes, we will be having the mid-side nodes also. Okay, so 1D beam elements we are having, and 2D triangular and quadrilaterals we are having, and in 3D tetrahedron and hexahedron elements we are having. Okay, since we are going to demonstrate on a 3D geometry, you should remember these two things. So tetrahedron elements, hexahedron elements, or this one, these are pentahedron elements or nothing but the wedge shaped elements. Okay, so just remember, focus on the 3D elements. So tetrahedron elements, so that will be of this triangular shapes, and hexahedron elements, it's like a cube. You can remember like a cubical elements, and wedge elements. Okay, so just focus on these 3D elements. And this is a representation of your geometry. The elements are based on the geometry. So if you are having 1D geometry, like truss structures, if you are having, so if you are having a truss structure, so truss structure will be we will be using beam elements for discretizing the truss structures. And if you are having thin objects or nothing but if you have a car door or car outer surfaces, so those are like thinner parts. So those parts we will use shell elements for discretizing. Then again, solid elements. Okay, so any 3D object we can have based on assumptions, we can use solid elements, shell elements, and beam elements. Okay, so there will be some assumptions behind identification of the solid, shell, or beam elements. Let's see about those assumptions. Okay, any 3D object can be converted into 2D object. Okay, if it satisfies a few assumptions. Okay, so what I'm saying, generally any engineering problem, if you take, that is a 3D only. Okay, it is not a 2D or 1D. So any problem, it's generally 3D only. But if it satisfies a few assumptions, then such 3D object I can treat it as either 2D or 3D. Okay, so in this slide you can see any 3D object can be converted into 2D object if it follows some assumptions. Okay, so when I can say a 3D object that can be treated as a plane stress state. Okay, so if your 3D object, okay, let's say the thickness is very small, so that means thin structure. Okay, if your thickness is very small and loading is on the plane, that means if you have a plate and it is loaded in the plane direction, it's like a stretching of the plate. Let's imagine like that. Okay, if you have a plate, when it is stretched, that means the loads are along the plane and there are no loads perpendicular to the plane, and the thickness of the object is small, then such a 3D object can be treated as a plane stress state. Okay, you can see stress components perpendicular to the 2D plane are negligible. That means there are no loads on the perpendicular direction of that plate. Okay, such cases, if the problem is satisfying, then we can treat that 3D object as a 2D object and we can name it as a plane stress state. Okay, so thus examples will be beam, plates, shells, and membranes. Okay, in the same way, those 3D objects which satisfy the assumptions of the plane strain state, you can imagine like a long beam, long dam. Okay, long dam, long pressure vessels, long pipes carrying fluids. Okay, so those kind of cases, those are generally long dam means it is a 3D object only, but we will treat it as a plane strain state. Why? Because let's say this is a long dam, so this is a dam. So if you take the cut section of a dam, okay, so on that cut section of the dam, okay, the perpendicular direction, if you see, let's say that has a thickness, if I call, so the thickness is not smaller, so it has so much length. Okay, the thickness is not smaller. Okay, long dam I'm saying. Okay, so that 3D object, if it satisfies few conditions, like again here also, the perpendicular the cut section, if I take, the loading should be on the plane only. Okay, the perpendicular direction to that plane should not have any load. Okay, such cases, if it is having, then I can treat that 3D object as a plane strain case. Okay, in the same way, 3D objects can be treated as 2D axisymmetric analysis if it follows three types of assumptions. That is, along the that means around the axis of that object, if the material is symmetric, if the geometry is symmetric, if the boundary conditions are symmetric. Okay, if those three conditions are satisfied, then such structures I can take it as a axisymmetric analysis case. Okay, so purely there is no 2D or 1D case. So it is like a representation of the 3D object into 2D or 3D, 2D or 1D, if it satisfies few assumptions as mentioned here. Then one more thing we need to remember about the free degrees of freedom on a particular node. Okay, so this is the this is the hexahedron element. It has totally 8 number of nodes. Okay, so it's a linear element. Why? Because only nodes are there, only corner nodes are there. There are no mid-side nodes, so that's why it's a linear hexahedron element. Okay, it has 8 number of nodes, and at each node we should know what are the degrees of freedom. Degrees of freedom means possibility of that particular node to move in a particular direction. Okay, so degrees of freedom, a solid element can have, it has 3 degrees of freedom, so namely ux, uy and uz. If it is a 2D case, then you will have only 2 degrees of freedom per each node. Okay, so it's a 3D case and it's a hexahedron element, so it's a solid hexahedron element. So each node will be having 3 degrees of freedom, that is translation degrees of freedom ux, uy and uz. Okay, so likewise based on the element you'll be having the degrees of freedom per each node. Okay, if it is a solid element, then definitely it will have 3 degrees of freedom. Okay, if it is a shell element or beam element, okay, if it is a 3D shell element or beam element, so definitely each node it will be having 6 degrees of freedom. That means 3 will be display, 3 will be translation degrees of freedom, and 3 will be rotational degrees of freedom. Okay, so just remember, if it is a shell, it will have 6 degrees of freedom. If it is a solid, each node it will be having 3 degrees of freedom. Then there are some advantages and disadvantages. So disadvantages means if you have a good hardware, so these are not a disadvantages. Okay, so advantages means, you know, any kind of complex geometry can be tackled. So any kind of nonlinearity in whether it is nonlinearity in material or geometry, that can be handled. Okay, and any kind of boundary condition can be applied. Okay, so commercial codes can handle general class of problems rather than requiring different programs for plane, axisymmetric, and 3D, etc. cases. So what it is saying, so a good software can deal any dimension. That means whether it is 1D, 2D, or 3D. So single software can handle these 3 different domain case problems. Disadvantages means, so the first thing is it is a numerical method based. So FEM is a numerical method. So numerical method, the solution will be approximate. Okay, so they are not accurate always. Okay, so they will be approximate. Okay, so that is, the solution is numerical rather than analytical. So significant computational resources are required, because if you are having so many number of nodes and elements, then definitely you should be having a good software, a good hardware. Sorry, large amount of input data may be need to be stored. Why? Because if you have a large number of elements, then definitely you will be having lots of memory to be utilized, and large amount of output needs to be stored. Okay, that is also one requirement of having a good hardware if you are handling with big problems. Okay, so those are like, you know, it's like a simple hardware cannot handle a big complex problem. That is what the disadvantages it means. Then coming to the workflow in the simulation. Okay, so this is earlier I told you about some equation, that is k into u equal to f. That is the finite element equation for a single element. Okay, so finite element equation. Okay, so for a single element, we are going to develop this equation. Okay, and ultimately we have to combine it. So that means so many such equations will be there, because so many elements will be there. So each element will be having this finite element equation. Combining all those equations, definitely we will have a, you know, so many number of finite element equations combined together. So that we will say it as a global stiffness matrix. Okay, so the green colored box you can see, that is a combination of all those equations based on the nodes. Okay, so this is a finite this is one equation. Okay, and this is another equation, and another finite element equation. Okay, so this assembly of the each individual finite element equation will be based on the nodal number. Okay, node numbering. So that assembly can be done based on the node numbering. Okay, so what I am going to tell you here is, each equation of a element, we will be having so many number of such finite element equations. All those equations we have to assemble to have a global stiffness matrix and global finite element equation. Okay, so you can see the boxes mentioned here. So those are related to the those are representing the global finite element equations. Okay, so green color one is the global stiffness matrix, and blue color one is the global displacement vector, and red color one is the global load vector. Okay, so this is a matrix, and this is a vector, and this is again a vector. Okay, based on your problem domain, we will be having the size based on the number of elements and number of nodes. Now, just focus on this one. So this is a logical analysis routine of your of any problem. If you take the step-by-step process, you can understand from this slide. Okay, we will start with material definition. Okay, generally structural steel or aluminum. Okay, so those kind of engineering materials, we have to provide the data of those engineering materials. So that is a material definition. We have to define the material definition. It will be done by means of the engineering data. So engineering data cell will be there. So this is a analysis system. Let's say static structural is the analysis system. Okay, it is followed by some different cells. So starting with the first cell, so engineering data, we have to provide the materials data, and in the second cell is the geometry. So you have to create the geometry. If you have the geometry done in some different CAD software, so you can import it. That can be done here. Otherwise, Ansys is also offering 3 different CAD packages. There also you can do the CAD modeling. So SSC is the space climb. Earlier I showed you about discovery. So you can use either discovery or space climb to create the geometry. Otherwise, if you have a geometry made in some third-party CAD tools, that also we can import it. Those facilities also Ansys is offering. Okay, so the geometry preparation is second step, and third cell will deal about the model. So you can understand from the figure here. So it is like cutting the geometry or splitting the geometry. So that is what we say is a meshing. So in the third cell, we will do the meshing. So the robust meshing capabilities is Ansys is offering this kind of a robust meshing. So sometimes it is manual, and of course automatic meshing is also possible. Then again, coming to fourth one. So in the fourth step, what we will do, we will apply the boundary conditions, whether it is structural or thermal or fluid boundary conditions. Okay, so those boundary conditions we can set up from the fourth cell. Then coming to the fifth cell, so that is the solution stage. So based on the physics, you have to identify the appropriate solver. Otherwise, simply there will be a thunderbolt symbol option. So you can select it accordingly. It will be solved. Okay, we don't need to develop the finite element equation. We don't need to assemble it. Okay, so those things we don't need to do. Software will do it in the backend. Then coming to the sixth one, the sixth step, you can identify based on the solution if the solution is done without any errors and warnings. Okay, so warnings generally we don't need to worry. So there should be no errors. So once the solution is done, you can check your results like displacement, stresses, strains, temperature plots. Those pressure distributions. So all those things you can identify from the sixth cell. Then coming to the seventh cell. So seventh cell, it is a parametric analysis thing. That means multiple load cases if you are having on a same structure. If you want to know the responses on responses with respect to the different load cases. Okay, so that can be done using the parametric studies. Hope you should give some time on understanding this slide, because if you are new to the Ansys software, then this slide will be the first stage for you to start learning. Any doubts are there, you can text in the chat box. Otherwise, you can unmute if it's possible. You can unmute and you can ask your questions.
Yeah, I have mentioned that to them, Shyam, in the chat below.
Yeah, perfect, Venkat. Thank you. Now same routine I'll be showing you in a different view. So what we will do, we have to call the analysis. So simply static structural analysis we have to call, and we have to follow all these cells correspondingly. Okay, so what we will be utilizing, I will be going to the Ansys workbench. Okay, I'll call the Ansys workbench, I'll open it, and I will be having a project page. Okay, there I have to identify what type of analysis I'm doing. Okay, so based on the mechanics, temperature involvement, and static and dynamic cases, accordingly I will identify the type of analysis. Okay, that can be done using the Ansys workbench project page. Okay, then again, material definition, that is the first cell, and geometry import or geometry creation, that is the second step. So this is the first cell, this is the second cell. Okay, then file management. Okay, so once you input the material, once you call the geometry by means of importing, okay, then the CAD model is ready, once the CAD model is ready, so we will be jumping into the Ansys mechanical. Okay, so that is the third step. Okay, so the third cell. So first cell is material definition, second is material import, and third is the third one is the model. So if you open the third one, so model, so you will be directed to the redirected to the Ansys mechanical. There, what you have to do, you have to assign the material property. Earlier you defined it, but you have to assign the materials corresponding to the geometry. Okay, corresponding to the parts of the geometry. Okay, so if you are having any thickness, so you have to mention the thickness. If it is a 2D geometry, you have to mention the thickness here. Then some simplification on the geometries may be required. So defining the point masses. Okay, sometimes connections also you have to provide. So joints and contacts, those are called connections. Okay, then again discretization, that is nothing but the meshing. Okay, so just remember, discretization means it is nothing but the meshing. Okay, so all these things will be done in the third cell, and in the fourth cell the boundary conditions. So apply the boundary conditions according to the analysis what you are doing. So boundary conditions can be of two types. So just remember, there are two boundary conditions will be there. That is displacement boundary conditions and force boundary conditions, nothing but the load boundary conditions. Okay, so boundary conditions will be are of two types. So we have to define both the displacement as well as boundary load boundary conditions. Once you do the fourth cell, so that is the fourth cell is nothing but the boundary conditions. Once you establish that one, you have to solve it. Once you solve it, background, you will be there will be some set of files created. So ds.dat will be created, and if it is a structural problem, file.rst will be created. If it is a thermal problem, it is a file.rth will be created at the background. Okay, so for solving all these things, the solver behind is the Ansys mechanical APDL. This is the solver which mechanical will be using generally. Okay, then once it is done, so fifth step is the result viewing step. So sorry, fifth step is a solution step. Okay, once you solve it, these files will be created, and in the sixth step, what you have to do once the solution is done, you have to identify the deformation, stress strain plots and diagrams, plots, pictures. Okay, you can write the report as well, and you can keep the probes also at a particular location if you want to see. So you can use the probes also, probe, maximum probe tools, minimum probe tools, all those things Ansys will give you to choose. Then coming to the different types of structural analysis what we are having. So as I told you, structural analysis is like two varieties. One is implicit structural analysis and explicit structural analysis. Okay, in the same way, depending on the time frame of the problem, so there are different classification, you can see it here. So statics problems and dynamics problems. So statics problems means the loads will not vary with respect to time, and dynamics means the loads on the structure will be varying with respect to time. So statics means loads are not depending on time, whereas dynamics, the loads will be depending on the time, depends on the time. Statics, it does not depend on the time. Okay, again, based on the linearities and non-linearities involvement, so we can classify linear and non-linear. Okay, and coming to the dynamics, so all the cases will be mostly linear dynamics cases. Okay, so in dynamics cases, again, based on the domain, frequency domain or time domain, we are again having the split. Okay, so if it is a frequency domain, okay, that means in dynamics, what generally we will be having displacement, stress, displacement, velocities, and accelerations. So if they are if some certain assumption is there on those three things, then that domain we say is a frequency domain. So in frequency domain, displacements, velocities, accelerations will have some assumption. Okay, if that assumption is not there, we say it as a time domain. Okay, so in frequency domain, again we are having some separate classification: pre vibration and post vibration. So pre vibration case, we generally say it as a modal analysis. Okay, so using the inputs and outputs of the modal analysis, we can perform the post vibration case. So again, post vibration case, we have three cases: harmonic, random vibration, and response spectrum. But anyway, in this slide, for this session, we can only focus on two things. One is static structural case. Okay, whether it is linear or non-linear, both the things can be handled. Okay, and this one, modal analysis, that's a free vibration case. Okay, so one static analysis case and one dynamic analysis case we will be having as a demonstration today. Okay, I'll take further some 5 to 10 minutes, and I'll wind up these slides and I'll go to the demonstrations. Okay, then linear analysis and non-linear analysis. Just a minute. Yeah, better I'll jump to the static and dynamic analysis case. Okay, so this equation you already saw in the previous slides. I told you this is the finite element equation. Stiffness multiplied by the displacement equal to force. Okay, so if it is a statics case, okay, forget about the hiding here. I'm telling about the statics case here. So in static analysis case, this is the finite element equation. K into U equal to F, where F is the not depending on time. You can see F is not depending on time. Force is not depending on time. That is a static analysis case. Okay, so what are the features of this static analysis? Loads and responses are not depending on time, and loads applied gradually, quasi-static process, and it does not account for mass and inertia of the it won't consider the mass and inertia effects. Okay, that's why from the equation you can understand there is no involvement of density or mass. Okay, so strictly mass and inertia of the bodies are not required in the static analysis. Okay, then material properties will be Young's modulus and Poisson ratio. Okay, so Young's modulus and Poisson ratio, these two things are definitely we need to include. Okay, so that is about the static analysis. Coming to the dynamic analysis, the equation is not simple. Okay, earlier if you see the static analysis, it's a simple equation, but here in the dynamic analysis, it's not a simple equation. So the complete equation is this one. So it will have masses, it will have damping, okay, along with stiffness and displacement and forces. It will have mass and stiffness matrices. That means inertias and damping forces will be involved. So, and if you see the forces, since it is a dynamic case, so dynamic case means the loads will be depending on time. That's why the force is having the dependency on the time. Okay. So in dynamic situation, loads are not loads will be definitely depending on time. Okay, so mass and dampings of the system is considered. That is m into u double dot plus c into u dot. So that is the mass and dampings of the system. Density of the material is required. Why? Because mass is existing. That's why density is required in the dynamics problems. Okay, so problems can be classified in two ways: frequency domain and time domain. So I already told you frequency domain means you will be having some assumption on displacement, velocity, and acceleration. Okay, that type of assumption will not be there in the time domain problems. Frequency domain, we are having different cases, so harmonic, random, and response spectrum. So all these cases, if you want to do, you need to first of all you need to perform the model analysis. That's the free vibration analysis you have to perform. Okay, since so many analysis we are having, okay, so if you want to have a stronghold on all these types of analysis, Ansys is offering knowledge resources to you. So you can see Ansys innovation courses is one thing. So Ansys innovation courses, if you go there, you can find a lot of courses based on your interest. You can classify. Okay, then that is what about Ansys innovation courses. Then one more thing, Ansys help. So if you search Ansys help in your internet, you can be redirected to Ansys help public domain. Okay, there you can download so many documents and examples and step-by-step tutorials also you can find there in the Ansys help. Okay, along with that, we have Ansys Learning YouTube channel. Okay, you hope you might have seen the Ansys Learning videos in YouTube. Okay, then coming to the Ansys innovation courses, earlier I told you this is one thing. Ansys innovation courses, based on your physics, you can have different course categories. Okay, so fluids and structures and electronics. Okay, along with that, it has categorized the courses based on the student teams. Okay, so if you are having aerothon, if you are involved in aerothon or SAE, different competitions, if you are involved, so accordingly, ANSYS innovation courses will offer you the courses according to the competition. So ANSYS innovation courses, student teams, if you see, just now I mentioned you. So based on your competition, you can find relevant courses, and all these courses it is free. So you don't need to these are accessed freely. Okay, so what you can have from these Ansys innovation courses, you can see the videos, you can download those sorry, you can download the simulation files also. Okay, so input files, output files, you can download from the Ansys innovation courses. Okay, that is a benefit for the students. Okay, now coming to the demonstrations, as I mentioned, we are having two types of demonstration. One is static structural analysis on the hexacopter. Okay, so this is the first demonstration, and second demonstration will be model analysis on the same structure. Okay, so these two demonstrations we will be performing in the next 1.5 hours. Okay, and after that I will just to show you the best practices of for finite element analysis. Okay, any questions are there? You can post, you can paste it in the chat box. Okay, quickly I'll be going to the first demonstration. Okay, let's understand about the first demonstration. So static structural analysis of the hexacopter. So static structural analysis, so it's a static analysis. So static analysis means we know the equation K into U equal to F. Okay, there will be no involvement of mass or density. Okay, so if at all the problem is having such things, you don't need to worry about it. Okay, that is about the superfluous data. So if you are performing static structural analysis, including mass and density, that will not affect your solution. That is what I'm saying. Okay, so as I mentioned you, in finite element analysis, we'll be having 3 steps: pre-processing, processing, or solution stage, and post-processing. So pre-processing, what we will do, we have to construct the entire problem. So we have to give the material as aluminum. So aluminum material we need to call, and hexacopter mass 2.55 kgs. Okay, then payload mass. So what we are going to do, we are going to use the payload mass. It can be a camera or any kind of goods. Okay, so let's say 12 kgs case I am considering. So 12 kgs payload I have to carry, and I will treat the contacts between all the parts interconnected between them as a linear contacts I will consider, and I will utilize the mesh density or mesh body sizing as 4 mm. Okay, so these are the inputs for the I mean these are the pre-processing steps. Okay, then once the problem construction is done, then you give the loads and boundary conditions. Okay, boundary conditions also it is kept in the processing stage. Okay, so what are the boundary conditions? That means 2 types of boundary conditions will be there: boundary condition, forced boundary conditions, and displacement boundary conditions. Okay, so forced boundary conditions, if you see, thrust force 16 newtons on each motor, we have to give the load 16 newtons on each particular each motor or each thrust generating object we have to identify. There we have to provide the thrust force, and payload force also we have to provide. Okay, so these are the two type of two things, two type of loads are there: thrust force 16 newtons on each motor, that will be acting upwards, and payload force that will be acting downwards. Okay, and one more thing is these are the two loading cases or loaded boundary conditions. Okay, then displacement boundary conditions will be the fixed support. Okay, so bottom we are having 2 phases, so we will select the bottom grounded parts will be there. So those things I'll take it as a fixed support. Okay, so whatever the parts which are touching on the ground when it is on this ground, when it is on the surface, so those things I'll take it as a fixed supports. Okay, that is the displacement boundary condition. So that is the processing stage, and once we solve it, we can go for the post processing. There you can see what are the stresses and deformations inside the entire assembly. Okay, so this is the first demonstration case. Okay. I'll tell you about setting of this environment later.
Yeah,
But
Shyam,
first of
there
all,
is one
yes,
person who's put up their hand.
yeah.
Tyagarajan, want to unmute yourself? Tyagarajan, you can unmute yourself and you can ask your question.
Hello. Yes, Tyagarajan. You need to
Yeah, or
unmute
you can even
yourself.
post your question in the chat window. Not a challenge. Both
Am I
ways.
audible now? I'm sorry for
Yes.
the inconvenience.
Yeah.
Sorry. Yeah. So I was wondering, a typical simulation like this, how long will it take? Because our systems won't be as efficient as like a workbench that you would find in a typical lab.
Okay.
So I was
Yeah.
wondering how much computation power we would require for running a simulation like that.
Yeah. Just you can identify from my system. You can identify how much time it could be required for you from your side. Okay, I'll show you those things. Okay, I'll address you after finishing the first simulation.
Oh,
Those
sure,
things.
sure.
Okay. Yeah.
Yeah, and probably you can share your system information also when you can, I mean, once you're done with that simulation, Shyam.
Sure. Yeah. So this is a typical model of our hexacopter. So this has been obtained from
Are
one
you
of the
sharing your
internet
screen,
source.
Shyam? Are you sharing
Oh,
something?
sorry. I just a minute. Yes. So this is a hexacopter geometry. I just showed you in the demonstration. Okay, so this has been downloaded from one of the available sources on the internet. Okay, so even you can also download those things. Okay, and no need to worry. I will share the simulation files as well with you. You can work it on the same geometry. Once we finish this session, I'll share all those things, relevant information to you. Okay, so this is an object. So we have to perform the static structural analysis. Those load cases I already showed you in the slide. Okay, so let's see how to create this entire environment. I'll show you. Okay, just let me close this. Okay, already I have solved the problem. I'm just showing it to you. Okay, again I'll construct everything from the scratch. Okay, so first of all, what we have to do, we have to call the Ansys structural. Sorry, Ansys mechanical. We need to open Ansys mechanical. So once the software is installed, you need to open the workbench. Okay, sorry for the inconvenience. So it is some different system I'm using. It is not showcasing directly. Okay, what I'll do, I'll utilize the workbench directly. Okay, so what you can do, you can search it from your system once the software is available to you. You can search workbench, then open the workbench, then you can see this kind of a project page. Okay, once it is open. Okay, so in the project page, what is the first thing, you have to identify the type of analysis what you are doing. Okay, let's say I'm doing the static structural analysis. Okay, so first thing will be identification of your type of analysis. As mentioned to you, structural analysis will be of different categories. Static structural analysis. Okay, again, dynamic structural analysis, we have different cases. Modal analysis, harmonic analysis. Okay, so those kind of analysis you can find it from here. Different type of analysis. Okay, so just what you have to do, you have to simply drag and drop it. So static structural, drag it and drop it. Okay, so that's a static structural analysis. Okay, in the same way, if you want to do the modal analysis, what you can do, you can simply drag and drop it. So static structural analysis, modal analysis. Okay, in the same way, if you want to do the harmonic response analysis, that also you can identify from here in the analysis system, drag it and drop it. Okay, it is very simple to identify the to set the analysis system. Okay, anyway, I'll be starting with the static structural only. Okay, so whatever the developed things, I'm just removing it. Okay, so in the static structural analysis, this is our this is our analysis system. Okay, so then first step will be engineering data. Once identification of analysis, engineering data we have to give. So from the problem, what you can see, it is aluminum, it is mentioned. Okay, so I have to give the aluminum data. So engineering data I'll open. Okay, what you have to do, you simply double click the engineering data. Okay, now you can see a different window is open. Okay, so it is a library. We need to find the aluminum from the engineering data sources. Okay, so Ansys is offering a very different varieties of libraries. Okay, so I'll go to the engineering data sources. Okay, there you can see the different libraries here. So aluminum means it's a general engineering material. Okay, so I'll go to the general material class. Okay, in the general material class, we can see the materials available here. So aluminum alloy is there. Okay, so since it is readily available, I'll take the aluminum alloy directly. Okay, so aluminum alloy. So I'm taking this aluminum alloy. Simply plus symbol, you just add it, then bookmark symbol will be displayed. Okay, now you close it. Now you double click it. Now you can see aluminum alloy. Just now I've taken the aluminum alloy, and structural steel is a default material. Okay, when you open engineering data, when you take any analysis, the default metal will be static structural. Okay, but just now because of the problem requirement, aluminum alloy I have taken. Okay, aluminum alloy has been taken here. Okay, so aluminum alloy is our material for the all the geometries. Okay, if you don't want the structural steel, then you can remove it, delete it. Okay, now my analysis will be sticking with the aluminum alloy. Okay, otherwise if you have some different composite fibers, or you have some different composite environment with you, then accordingly you can define the material also. That means you can construct your own material. So simply if you are having CFRP material, or your customized material, if you are having, let's say A, B, C, some material is there, so you can define the material, you can insert the corresponding properties what you are dealing with. Okay, if it is a structural problem, accordingly the linear elastic data you need to input. Density, it is not required for the static structural analysis. Okay, so accordingly you can see the variety of properties here. So physical properties, linear elastic data. Okay, and again different material models also you can call it. Okay, hyperelastic material properties, viscoelastic material properties, and elastoplastic material properties. Okay, so variety of material properties also you can construct here. Okay, if you have a specialized material with you, you can do such things. Okay, so you can drag the material existing in the library. Otherwise, you can construct your own material also. Okay, so I'm just deleting it. So right now we'll be sticking with aluminum alloy material. Okay. So engineering data is done. So engineering data, just now we showed you aluminum alloy has been taken. Okay. Then coming to geometry. Okay. So if you have a geometry, okay, you can import it. Okay. What you can do, you can right click it and import the geometry. There is an option here, import the geometry. You can browse the corresponding file there. Okay. You can do it direct import. Okay. Otherwise, if you want to construct the geometry here in the Ansys environment, I told you already, Ansys is offering 3 different CAD environments. Okay, you can right click it and you can see the first 3. So you can open the
Shyam,
discovery. Yes.
sorry to disturb you. There is a request to just come that, they majorly will be using additive manufacturing and also carbon fiber as materials. So just help them as to how to go about that process also. No, additive manufacturing can be left out, but then materials across, say, carbon fiber, or if you can take up materials which are majorly to do with
Yes.
just teach them as to how to go about selecting the material.
Sure.
Thanks.
So I just showed you how to sort for the how to go for the aluminum alloy. Okay, in the same way, what other libraries we are having, I just showed you. Engineering data sources, if you go, so from here you can see the different classes of libraries I told you already. So just now we picked the aluminum alloy from the general materials library. Okay, in the same way, different classes, if you see, additive manufacturing materials are there. So from this class, you can see the variety of additive manufacturing materials. Okay, let's say Inconel is there. Okay, next TI6AL4V. So you might be knowing about this one, TI6ALV4. So this is a material generally used in high temperature applications. Particularly ISRO is utilizing this material for a vast variety of products, particularly storage of your propellant tanks. Okay, so those tanks are generally made of this TI6ALV4. Okay, those kind of materials you can identify from additive manufacturing materials. So additive manufacturing materials means, right? So conventional process, if you can't work with a particular material, then using additive manufacturing techniques, you can work with that materials. Okay, so that is an example for the TI6ALV4. Then coming again to the composite materials. So even composite materials, composite fibers are there. Okay, so composite fibers, different e-glass materials are there. Okay, epoxy, laminate materials are there. Okay, so you can see. So in the composites material category, you can see around 30 different type of composite materials are there. Okay, so what you can do, if you want to go with carbon fiber, so you can simply bookmark it. Okay, that will be taken to your engineering data. Okay. Okay, so again, in the same way, if you are doing any LS-DYNA problem, or maybe the explicit case problem, okay, so accordingly, explicit materials are there. Okay, you can see the materials for the library of explicit materials. It is, yeah. In the same way, fluid materials, thermal materials. Okay, so all those materials you can simply select it by means of the plus symbol here. Okay, accordingly you can utilize the variety of materials existing in the Ansys libraries. Okay, and again, Ansys Granta is a different library. Okay, so you can see the name mentioned here. It is a sample thing. Okay, so Ansys Granta offers you a 700 libraries of material data, but right now it is a sample data has been added in the engineering data here. So Ansys Granta material data, that is a simple data, a sample data it has been given here. Okay, so wide variety of industry available materials can be obtained from the Ansys Granta, and that too we are provided with some sample data. So 41 different sample materials are there from the Ansys Granta. Okay, so if you have Ansys Granta with you, 700 varieties of libraries you can access. Okay, and there is a separate separate selection criteria accordingly. Okay, so likewise you can identify the class of different class of libraries. Okay, so anyway, right now let's see what engineering materials we are having. See, just now I've taken carbon fiber. Okay, that's why these are available here. I'll just remove it. Right now it is not required from our in our analysis. Okay, but you can try from your side in your systems. I'll stick with only aluminum alloy. And as I told you, we have three different CAD softwares we are having. So Discovery, Space Claim, and Design Modeler. Okay, so you can start with anything if you are not familiar with CAD modeling softwares earlier. Okay, you can start learning from these softwares directly. So Ansys Space Claim is very much used in industries previously, but right now Discovery is a tool Ansys is highlighting to go for the CAD modeling. Okay, right now anyway, I have the geometry with me. So what I'll do, I'll just import the geometry. Yeah, I have the geometry now. You can see it's a hexacopter. I just showed you the geometry already. So it is done in the Space Claim software. So SCDOC, accordingly the name you can see. So hexacopter Space Claim. Now you can see the green color tick symbol. So which means the geometry is done. Geometry is ready. Okay. Then again, quickly I'll go to the next step. That is the fourth cell, that is model. So second one I just showed you. Third one, second one is the material, and this is the geometry, and the fourth one. So fourth cell, if I double click it, then I'll be redirected to the another window that is called as mechanical. Okay, right now what we are seeing, that is Ansys Workbench platform. But if I click the fourth one, the fourth cell, if I access, then I'll be redirected to the another window that is called as mechanical. So that is Ansys mechanical window. You have to wait until the red dot at the bottom disappears. You can see still the red dot is there. Okay, so in the workbench window, you can see the red dot. So once the red dot is disappeared, we are ready to use the Ansys mechanical window. So this is the Ansys mechanical window. Once the red dot is disappeared, we are ready to use the mechanical window. Since it is a big geometry, it is taking some time to convert it into the compatible way. Now the geometry has been imported here. Okay, right now what I'm using, it's a 2024 R2 version. Okay, so before I do anything, I'll do one thing. I'll reset the entire layout. Why? Because right now, whatever the layouts you are watching, that is a customized based on my work. Okay, what I'll do, I'll go to the reset layout that is existing in the home ribbon. So resetting the layout. Okay, this is how your system, once you open Ansys Mechanical, you will see in this way. So once I reset the layout, you can see the generalized thing. Okay, so reset the layout. Now if you see the outline from the left side, so the details of your model
particularly how many parts are there, what are the materials you are having. Okay, those things you can have the access from the left side, the project tree. So we say it's a project tree. Now you have the model. Okay, now step by steps, if you see geometry, there is a question mark symbol. Okay, let's see what is this question mark symbol. See, whenever there is a question mark symbol, that means it needs to be given, we need to provide some data. Okay, so something is missing, that's why the question mark is appearing. Let's see what is the question mark. Okay, now I will open the geometry and you can see so many parts are there. So many parts are there in this assembly. Okay, so everything is having a question mark, which means, let's see, if I select the main body. Okay, so the main body, the corresponding details of the main body you can see at the bottom. Okay, now you can see main body. Again, main body is having so many parts inside. Okay, so few are having question marks and few are having some tick marks, green color tick marks. Okay, so what I will do, I will give each and every part with the aluminum alloy. Okay, so what I'll do, I'll select the each and every part. Okay, I'll select each and every part. Okay, for multi selection from the keyboard, you can select the shift option. Okay, so first part I have taken, and last part, before selecting the last part, I will use the shift key from the keyboard and I'll select the last one. Okay, so all the parts have been identified. So you can see in the details of the multiple selection, you can see something is missing here, that is the material assignment. So material assignment, what is the material assignment? I have to give the aluminum alloy. Okay, so now you can see there is no question mark in the main board. Okay, in the same way, remaining parts also I have to give the aluminum property. Okay, so there again, aluminum propellers, all the parts I will take and I'll assign the material as aluminum alloy. Okay, then again, the propeller arm, here also I'll select each and every part and I'll take it as aluminum alloy. Okay, likewise, I will assign the material to each and every part using the aluminum alloy. All the parts aluminum. Again, propeller arms, aluminum alloy. So what I am doing, I am giving the material assignment. Earlier, what I did, I gave the definition of the material, but right now for every part I am assigning the material. That is aluminum alloy I have taken here. And again, hexacopter. For these parts, I'll give the aluminum alloy. Okay, now you can see the geometry. The symbol is updated from question mark to green color right click. Okay, then again, materials. We know materials. We have aluminum alloy material. Okay, then coordinate system, no need to worry about disturbing. Now coming to the connections. Now you know all the parts you can see, they are connected with each other. Okay, so the propellers, the shaft, motors, arms, frames. Okay, so all those things are, it's a big assembly. Okay, now I'll show you one thing here. So how the parts will be in the exploded view. Now simply go to the display. In the display at the end, you can see there is an explode option. Now you can do one thing. You can move the slider and you can see the exploded view of your parts. So all these parts have been connected internally. I'm just showing you for the visibility purpose, the exploded view, I'm just showing it to you. Okay, so all these parts have been connected with each other. So we have to define the connections between them. Okay, for simplicity, simplicity case, what I'll do, I will consider all the contacts as bonded contacts. Okay, that's a linear contact. Okay, so all the contacts between the parts, I will be considering it as a bonded contact. Okay, and that is the automated step actually. So once you import the geometry, the connections will be automatically existed, and all these connections by default will be bonded only. Okay, so connections, hopefully you might have understood. So all the types will be bonded contacts. Okay, all the contacts will share the bonded contacts, but it is by default. I didn't give this. Okay, so it is by default automatic connections will be there. So I'm just not disturbing the connections between each and every parts. All the connections are bonded contacts only. Okay. Now coming to the next step, meshing. Okay. So it is mentioned the meshing, what meshing we have to use. You can see it here from the problem description. So this is our problem. Now you see aluminum, we have to take the aluminum. Okay, but right now I am just using aluminum alloy. It is readily available with me. So aluminum alloy I have taken. Then what is the hexacopter mass? So 2.55 kgs is the mass. So I have to ensure the entire hexacopter should have the 2.55 kgs. Okay. So I'll just check once what is the mass of it. Okay. So since it is a aluminum, if it is a aluminum, then it will be 2.55 kgs. Now let's see what is my geometry shown. Okay. So I'll go to the geometry. Now you see geometry. In the geometry, if you go to the details of the geometry, their properties you can access. Now you can see the mass is 2.5509 kgs. Okay. So aluminum alloy also I can take. Why? Because aluminum or aluminum alloy, the mass should be 2.55 kgs according to the problem description. Okay. If it is something some other material, then the mass will be varying accordingly. Okay. So right now we don't need to worry about the material, whether it is aluminum or aluminum alloy. Mass is 2.55 kgs. So it's done. Then again, payload mass will be 12 kgs. So payload mass I have to consider 12 kgs. 12 kgs into force I'll be converting it to force. So 12 kgs into 9.8 or otherwise 10 I can take. So 120 newtons will be the payload. Okay. Then again, contacts will be linear contacts. I told you bonded contacts. Ansys by default it will create the bonded connections between them. So all those connections are nothing but the linear contacts. Okay. Then coming to the mesh, I have to give the body sizing of 4 mm. Okay. So body sizing of 4 mm I have to give. So in the meshing, okay, meshing will have two type of controls. So global mesh controls and local mesh controls. Okay, directly by selecting the mesh, the bottom you can see the details. So all these controls are called as the global controls. Okay, so global controls, I am not going to touch the global controls right now because in the problem it is mentioned body sizing I have to take. Okay, so I'll go to the meshing, I'll right click, insert and body meshing or nothing but the body sizing. Okay, so sizing I'll take, and sizing I'll select each and every part. Okay, all the parts I will select. Okay, what I will do from the keyboard, I will select in the GUI Control A. Okay, Control All, nothing but the Control A. So you can see 119 parts are there. Just a minute. I have to select the bodies here. So what I'll do, I'll change the mode to body selection. Okay, so this is the graphics toolbar. Okay, from the graphics toolbar, you will be having the selection option here. Okay, so you can select either a single point selection, otherwise voxel selection is also there. Okay, now again, selection tool, if you see, you can select vertices, edges, faces, and body. Okay, what I need is a body selection. Okay, so I'll select the bodies and I'll select each and every body by selecting Control A from the keyboard. Okay, that's one way. Otherwise, using your mode box select I'll take, and I'll select all entire box considering all covering all the parts. Okay, now it is having 119 bodies I'm having. So all those bodies I am selecting for this sizing. Now you can see. So what I am doing in meshing, I have created the local control, that is sizing control. Okay, by means of sizing control. Okay, I have selected the 119 bodies. That's why the sizing has been named to body sizing, because body selection tool is active. 119 bodies are there. Now coming to the element size, I'm keeping it as a 4 mm. Okay, 4 mm element size I'm taking. Okay, now this is a 4 mm. That's it. I'll try to mesh it. Okay, I'll update it. There is some problem. Now you see only few parts have been meshed properly. Okay, so according to the problem description, by simply going to the body sizing of 4 mm, it should give the it should give the entire machine. Okay, but right now a few parts are not able to mesh properly. Okay, what could be the reason? Any guess? You can text it in the chat box. I'll read it in the at the end. Okay, so what could be the reason behind not having the mesh properly? Okay, so there is a failed mesh. We can find it on the geometry on this GUI. So what could be the reason? You can text it in the chat box. Okay, so all the parts we are not able to do the mesh. Okay, so that is there are different options will be there for not having the proper meshing here. So one could be one reason could be the improper model. Okay, if
Yeah,
you are
Shyam, we've got one response. It says geometry where it failed is complex or the mesh size is too large. Still a
yeah,
nascent
yeah,
answer.
yeah.
Yes.
So the geometry is complex, you are saying, but what I will tell you, you did not do the CAD modeling properly. That's the best option I can tell. Okay, so this geometry, it is not able to give the proper meshing. Why? Because you did not do the geometry proper. That is one reason. Okay, there is another reason could be the other thing, like it is whatever the mesh sizing I am giving, it is not able to consider that mesh sizing for doing the meshing. Okay, that is also another reason. So, but first reason would be you have to identify whether the model is developed properly or not. Okay, why? Because right now the model I am having, there are some geometry is having some loopholes, so some geometry is not done properly. Okay, so there is cleaning of geometry is required before you start doing this machine. Okay, so geometry cleanup is done by means of, again, going to the space plane. You can do the geometry clean. Okay, so that is a thing. So if you are unable to do, if you're not having the proper geometry with you, then these kind of errors will be appeared, so you can't do the proper meshing. Okay, so you need to take care of the geometric modeling properly. Okay, so right now what I'll do something, and I'll do the meshing. Okay, so I know where the problematic area is there. Okay, I'll just show you. So this is one problematic area we are having. Okay, so this is one problematic area. I'll just show you the geometric view. Now, if you see, this is one thing. Okay, so it should be a perfect circular cylinder. Okay, but instead, what you see, sorry, box selection tool, it's a single select. So it is not a single circular cylinder. Okay, it is having some edge unnecessary feature, or nothing but the extra feature is there. Okay, so which is making my mesh to be ill conditioned. Okay, so and we are unable to generate the mesh properly. Why? Because of the existing of this particular geometry. Okay, so that's why while creating the geometry, you need to ensure this kind of unnecessary geometries we should avoid. Okay, so duplication of these geometries or uneven duplicate features like extra edges, extra points, extra faces, extra volumes. Okay, interpenetrations. Okay, between the parts, interpenetrations. Okay, all those things you need to avoid. Okay, then only you can do the meshing proper. Okay, that is what I'm telling you. Okay, so you need to be more cautious about creating the geometry. Okay, so that is one aspect, and one more aspect is there is one more difficulty is there in this geometry. I'll just show you. Yeah, now you see. Now you can see, you can identify this is a half of the half circular section, but now you see it is not defined properly here. Okay, so there is some geometry misalignment here, so it is not having the proper geometry. That is also one mistake from the geometric model. Okay, so because of such things, you are having some errors in generating the mesh. Okay, so That's why you're unable to do the meshing here. Okay, so what I'll do the selective meshing here. So I'll go to the body selection tool and I'll select this object and I'll operate generate mesh on the selected bodies. Now you see earlier there is no earlier there is a problem on that particular part. Now you can see there is a generated mesh on that part. Okay, then again coming to the another body, I'm selecting and I'm right clicking and I'm generating on that particular body. See, it is not giving you the meshing here. Earlier this part we can see the generation of mesh, but now here on this geometry there is no mesh generated. That's why, because I already showed you something is wrong with the geometry. Okay, so what I'll do, I'll use the virtual topology. I will activate here. Why? Because one thing what you could do is you have to go back to the previous steps. In the geometry step you have to go and you have to rectify the geometry. Okay, otherwise one more option is using the virtual topology. So using the virtual topology also I can do it. So what I'm showing you, virtual topology, it is another way of tackling this error in the mesh. Okay, so virtual topology I'll activate. Okay, in the virtual topology, so I'll highlight where this problem is happening. Okay, yeah, this one. Okay, so I'll go to the selection this side. Okay, I'll from the keyboard Control M. I'm going to create the virtual geometries. Okay, so by using virtual topology, what you can do, this kind of unnecessary features, we somehow avoid. We can avoid this kind of uneven geometries somehow. Okay, so I'm selecting these two surfaces, and from the keyboard, Control M. Now you can see virtual surface has been created. Okay, by removing the unnecessary features. Okay, so what I did, I have selected the two faces nearby and I have opted the Control M from the keyboard. Okay, what it is doing, Control M means it will merge the two surfaces, making the single virtual cell. Okay, in the same way, this surface also I have to operate. Virtual topology on the ill conditioned area, that is this one. Yeah, here it is. So I have to select two surfaces. So I'm in the virtual topology. Face control, face selection tool is active, and first surface and the second surface. Okay. Then Control M. Now you can see one more surface has been created, and you can see that different colored thing. So another virtual cell has been created. Okay. Now I will try to generate the mesh here. So I'll go to the mesh. This is the paint mesh here on the particular object. So I'll select the body of that geometry. Now generate the mesh on the selected body. Now you see. See, by using the virtual topology, this is another way actually. So best thing is going back to the geometry phase and you sort out those ill-conditioned features. You remove those features and you come back here and you mesh it accordingly. Okay, right now what I am showing you, the virtual topology is another option. Without going back there, you can do the geometry simplification here. Okay, so in the same way, wherever the problematic area is there, I'll identify it and accordingly I'll apply the virtual topology there to have the meshing for that. Okay, even for this geometry also, I will try to generate the meshing on the particular geometry. See, now it is there. Now this one also. Okay, so what I'll do, I will just remesh it again. So generate the mesh entirely and I'll see if it is done or not. Okay, but few areas are there which is having some troubles. Okay, so this is another area. Now you can see, now you can understand. So this surface So the two surfaces I will select, and Control M is for the merging. Again, same, this one and the other surface. Control M, merge. Okay, so I just merged all the relevant surfaces, and I'll see whether meshing is happening or not. Okay, now there is some issue in the geometry. Okay, now let's see on the other parts. Now, in the same way, likewise, you have to identify all those parts and you have to generate the mesh on the particular bodies. Since the geometry is big, that's why I'm doing this all these things. So geometry simplification by means of virtual topology I'm doing, and accordingly, each and every part I'm generating the mesh on the particular parts. Okay. Once it is done, once all the meshing is done, okay, now you can see the green color tick here. Once all the meshing of the parts is done, then only you can see the green color tick symbol. Okay, right now we are unable to see it right because something is wrong with the geometries of the this particular motors. Done. Okay, so on this motor there is some problem. So using some virtual topology we can avoid that. So anyway, right now we don't have that much time to show you rectifying all those things. I'm just showing you virtual topology. By means of virtual topology, you can avoid, you can do such things. Okay. Okay. Now I'll go back to the other step. Okay. Meshing part, you can do it later. So virtual topology, by means of virtual topology, you can avoid such things. Okay. Likewise, each and every part you can generate it wherever there is a problem. You can go and generate on a particular part by simply selecting and right click and generate mesh on the particular zone. Okay. Yeah. Now coming to the another step. So once meshing is done, what is the next part remaining with us? Now you see here. So mesh body sizing, we have to give 4 mm. We did that. And later, what is the next step? That's the processing step. So in the processing step or the solution step, we have to give the boundary conditions. So boundary conditions means thrust force 60 newtons on each motor, and payload force will be 1/8 newtons. Okay. So before going to this one, few things we will focus. Now you see whatever the mesh generated, you can see the element counts here. So one that can be identified from once select the mesh, go to the details of the mesh. There you can see the node count and element count. Okay, node count and element count, and now you see show detailed statistics. Okay, now here I am just selecting the S. Okay, whatever the generated elements are there, that data you can see it here. So you have 10 noded tetrahedron elements of 56,000 and 20 node hexahedral elements of 16,000. Okay, wedge shaped elements are there. 15 noded wedge shaped elements are there. 7321. Okay, can you tell me what is the number 10, 20, 15? By the 10, 20 means, is it a linear element or quadratic element? Okay. I'm just asking you, these are the 3D elements, tetrahedron elements, hexahedral elements, wedge shaped elements. Okay, so can you tell me what is the name, or what is the linearity, or whether it is a linear element or quadratic element? Okay, 10 node tetrahedral element means, is it a linear or quadratic? You can type it in the chat box. I will read it at the end. Okay, so these are before going to that one, just to see the number of elements once. Okay, number of elements are 83,000, whereas the nodes are more than the number of elements. Okay, 26 or nothing but 2,63,000. Okay, so if you see this kind of variation, that means more number of nodes compared to the number of elements. That means your elements are generally they are quadratic, they are not linear elements. Okay, so if you are having quadratic elements, that means more number of nodes will be there compared to the elements general. Okay, so if more number of nodes are there, that means definitely you should be having a good software or good hardware to proceed with. Okay, so if you are having the student version software with you, there is a limitation of using the number of elements. Okay, so 512,000 elements. Okay, or otherwise 5 lakhs 512,000 elements, or maybe
I put that in the chat, Shyam. I put that in the chat.
yeah. So you should be careful while selecting the or generating the number of elements. Okay, just now I'm using 4 mm size, right? So 4 mm mesh size I'm using, body sizing 4 mm I'm using. So accordingly, probably I may have once if I generate all the elements, all the parts, if I mesh properly, then hopefully maybe some 1 lakh elements I may generate. Okay, so that is the that is the way we can control the number of elements. If it is a student software, the generation of number of elements will be in your hand, whether it is a student software or whatever it is. So we will be having the control of controlling the number of elements and number of nodes. So number of elements you can control by means of local controls or global controls. And just now the body sizing you are watching, that is a local control. In the body sizing you can see that's a 4 mm. Okay, if you want to reduce the number of elements here, so what you can do, you can increase the element size here. So increase the element size here. Okay, each and every element, if you increase the size of the element, then obviously the entire geometry can have a less number of elements compared to the 83,000 right now what we are having. Okay, if you want to control the number of nodes, what you can do, you can switch it to the linear elements. Okay, I'll show you where you can switch linear and quadratic elements. Just select the mesh. Okay, in the mesh, go to the display defaults. Now you see, so mesh display defaults element order you can see. So by default it is set to program control. So program control means by default it will take the quadratic nature. Okay, so by default it will give you, it is showing you the quadratic elements. Okay, if you switch to the linear elements, then accordingly you will be able to see the linear elements. Okay, so if you generate it, but anyway right now we are having some errors because of some problems in the geometry. I'll try to generate it. So I'm generating the linear elements right now, and just now you can see, now you can understand what could be the variation of elements and nodes. There won't be any change in the number of elements, whereas you can control the number of nodes here. So earlier with the quadratic program controlled option, you are having more than 2 lakhs. Right now, if I switch to the linear elements, now you can see the reduced in the number of nodes, reduction in the number of nodes you can see. Okay, so in this way you can control the number of elements and number of nodes. And if you want to see the number of elements and nodes, okay, now you see, now I've switched to the linear elements. That's why the number of nodes have been reduced. Earlier it is 10 noded tetrahedron element, but right now because of the linear elements existing, you can see the 4 noded tetrahedron. Earlier it is 10 noded, but right now it is 4 nodes only. So by this number of nodes also you can identify whether it is linear element or quadratic element. Okay, so that is about the statistics of the mesh. Okay, right now I already told you why the mesh is not having proper orientation here, because of some included geometry is not proper. That's why we are unable to see the meshing properly. So I already told you how to avoid those things. You can utilize the virtual topology. Otherwise, you can go back there and you can do the meshing. You can do the modeling properly. Okay, now coming to the what I'll do, I will just set up each and every step. And right now I have the already solved geometry I'm having. So I'll switch there and I'll show you the results there. Okay, now meshing is not done properly because I told you what is the problem. Now coming to the boundary conditions. So boundary conditions, you can see thrust force 60 newtons on each motor I have to apply. Okay, so I'll do that first. So thrust force 60
Shyam, just
Newton.
a time
Yes.
check. It's 4 o'clock. Yeah, we've got another
Yes.
40 minutes or so.
Yeah. I'll do it quickly. Within 30 minutes, we can close it. No issues. That can be
No
done.
worries. Take your time. Just wanted to give you a time check. Nothing else.
Sure. Yeah. Thrust force 60 Newtons on each motor I have to apply. I'll do that one. Now, where is the thrust force I can apply? Okay, each and every motor, the support of that motor I can select, and there I can give the support for the thrust. Okay, so what I will do, I will insert. Okay, I will insert a thrust force. So that means force I will select. Okay, so here what I will do, I will select the each and every geometry where the thrust force is generated. We know already thrust force will be generated from the motors when it is rotating. The thrust force will be generated. So the effect of that thrust force can be transmitted to the base of that particular motor. Okay, so this surface. Okay, so these kind of surfaces I will select, and each surface I will give the 60 Newton thrust. And just confirm it again. So 60 Newton thrust on each and every motor. Okay, so one surface I've selected. In the same way, all the six supports I will select. Okay, so bottom of the motor. So two surfaces, 3, 4 surfaces. So if you have a quadcopter, then 4 surfaces you need to select. Since I'm having hexacopter, so 6 surfaces I will select. So 6 surfaces I have selected, and I am giving the force using component form. So, and you can see z direction I have to select. So z direction is upward direction. The thrust force will be in the z direction. So I'll give the component of 60 Newtons on all those motors. Now you can see the direction of the thrust force. So the thrust force is acting on the bases of the each and every motor. So this is the surface. On the surface, the thrust force is acting. Okay. In the same way, I have to give the payload. So what is the payload here? So payload force is 118 Newtons. That means 12 kgs payload I'm having. So 12 kgs multiplied by the gravity. So it will be around 118 Newtons. So 118 Newtons payload I have to provide. So to the bottom of the structure. So this surface I will select. So on that surface, I will give the payload. Okay, it could be a camera. Okay, it could be any other particular payload. Okay, so generally it will be kept in this inside the circular region. Okay, circular space we are having. So in this space, the payload can be arranged. Okay, so that effect of the payload can be transmitted to the surface of this one. So on this surface, I will give the bottom payload. So downwards payload force I will give. Okay, so I've selected the surface, and I'm inserting another force, that is the downward payload force. So again, that will be in the by means of components, and that will be in the negative z direction. Okay, so z direction I'm giving it as minus 118. Now you can see the direction of that particular 118 Newtons. So that is the payload. The arrow, you can see the red arrow. So that is 118 Newtons. It is in the downward direction. So thrust force is in the upward direction, and payload will be on the bottommost downward direction. Okay. So each and every motor is generating 60 Newtons. Okay, and bottom payload will be 118 Newtons. Just remember, each and every motor is having 60 Newtons. So 60 Newtons multiplied by all the 6 motors. Okay, so that the payload can be taken to the our whatever the desired elevation. You can generate the thrust force accordingly. Now one is the thrust force. I'm renaming it THRUST, thrust force, and this is the payload. Okay, this is the thrust force and this is the payload. Now what else we have to give? So boundary conditions, loaded boundary conditions I have to give. Now what else? The displacement boundary conditions I have to give. Okay, let's say it's a static structural analysis. So I will consider the bottommost touching points. Okay, so this surface and another this surface I'll select, and I'll give the fixed supports for those two supports. So fixed support I'm giving. So I'm inserting fixed support. Those two surfaces have been identified and I selected. Okay, so that is about the displacement boundary condition. So with this, my entire steps are done. Okay, so you can see the green color symbols. So geometry is done, materials uploaded. Then again, coordinate system connections, all are linear connections. and meshing is not done properly because I told you there is some problems in the geometry. Okay, then again thrust force, payload force, fixed supports. Okay, all these things have been established. Okay, once you have a proper meshing, then you can solve, go for the solve. Okay, right now I don't have the mesh. I don't have a time also to mesh each and everything. So what I'll do, I'll stick to the already developed model with me. You can see it here. I have a good model with me. It is not having any such issues. Okay, so you can see geometry is done. Geometry, green tick, materials green tick, connections, mesh is done. You can see. So this is the mesh I'm having, and you can see the meshing here. So body meshing I am having. So now you can see the statistics. In the statistics, if you see, it is having 1,13,091 elements, and nodes also you can see 3,31,000. And you know, more number of nodes compared to the number of elements. That means we are having the program controlled element order. That is by default it's a quadratic. Okay, so quadratic elements we are having. That's why more number of nodes compared to the element number. Okay, now you see what could be the the fixed support we have given, payload we have given, thrust force we have given. Okay, so once you establish all these things, once meshing is done, now you see what could be the now I'll remove all these things. Okay, once you do that, once you solve it, what you have to do once you to solve it, for solving you can do this. I'll just remove the generated data. Okay, once you establish, once everything is done, green color, green mark is there, now you solve. Now you can see the mesh is having 3 lakhs nodes. The mesh is having 3 lakhs nodes, and I have selected 8 number of cores here. I'll show you once the solution is done. 8 number of cores right now I have selected, and now I am solving it. Now you can see what could be the solution time. Forget about the warnings. Now you see the solution is done. That's why you can see the right mark symbol, green tick mark. Okay, now the solution is done. How much time it took for me to solve the 3 lakh number of nodes? The model is having 3 lakh number of nodes, and I've selected 8 number of cores. Now you can see what is the elapsed time here. So 45 seconds it took to solve the entire model. It is a statistical problem, and just now I showed you the number of elements, number of nodes. You see 3 lakh number of nodes are there, and because of 3 lakh number of nodes, and with selecting 8 number of cores, my solution time is 45 seconds. Okay, but probably from your system, if you are having a personalized laptop or desktop, probably you are able to solve only 4 number of cores. Okay, 4 number of cores. Now I will try to solve it. I'll clear the entire data again, and I am solving it. Right now you can see it is 4 number of cores. So 4 number of cores I am using with the 3 lakh number of nodes. Now you can guess what could be the time. Earlier it is 45 seconds. Now it could be around some 5 to 10 minutes, or maybe less than that also. So Tyagarajan, you can understand. Number of cores you can utilize only 4 from your system. So the complexity of geometry what I'm having, it is 3 lakh number of nodes are there with 1 lakh number of elements. So it will take around some 5 to 10 minutes to give you the solution. And of course, there are some things, a few things you need to remember. All the connections are linear connections. That means bonded contacts. Okay, that's the one thing you need to remember. And material what we are having, that is aluminum alloy. That is the isotropic, elastic isotropic material only. Okay, if you want to keep your different material like composite material or any other hyperelastic material or maybe some elastoplastic material, if you want to keep, then accordingly the solution time will vary. Now you can see. Luckily, it took only 50 seconds. With the 4 number of pores, 50 seconds only the elapsed time. Generally, from your system, if you try, it would be around some 5 to 10 minutes. You will get the solution. Okay, if everything is having the green color tick mark, then you will definitely have on this particular model from your system. If you solve, it will take just 5 minutes to solve. Okay. Now, once the solution is done, what you can do, you have to identify what is the deformation, total deformation, and you can see the stresses. What is the stresses? Okay. Based on the generated stress, we can see whether we are in the safe region or not. Okay. So I will ask to evaluate the result. This one also I'll ask to evaluate the result. So generally, these are the two things we generally selected. Total deformation. Now you see the total deformation in the entire model. The total deformation of the entire model is, it's in mm, units in mm, that to 0.13. Okay. Now I'll show you this in the front view. Now you can see the animation here. Okay. But that is not the realistic view. So what I'll do, I'll switch to the results. There in the results, context results, there I'll go to the true scale. Okay, so true scale, and you can see the mm. So 0.1 mm. So from your naked eye, you can't see the deformation. So it will be like this. You can't see the deformation with the naked eye. So that is a true scale. That's why you're unable to see it. If I exaggerate it, now you can see some animated view. Okay. So with the boundary conditions, forced boundary conditions and displacement boundary conditions, you can see there won't be much deformation. Okay, you can increase the payload also. Accordingly, thrust force also you can increase. Okay, at 12 kgs it is safer because you can see the deformation. It is not much. It is not high value. 0.1 mm. It's a considerable thing only. And from the probes, you can see the probes there. Probe maximum and minimum. Okay, so maximum. Where is the maximum deformation and minimum deformations? We can see it from the same GUI. So you can see where is the maximum deformation. It is occurring at the thrust generating parts. So that is at the motors. You can see the maximum deformations happening, and minimum deformations will be, yes, obviously it will be at the fixed supports. So fixed support means the bottom parts are, we selected the bottom parts as the fixed supports. That's why the zero deformation is happening at the bottom supports. Okay, so maximum and minimum deformations we have seen using the probe options, maximum probe and minimum probe. Then again, coming to the equivalent stress. So all the parts are made of the aluminum or aluminum alloy. Okay, now you see maximum stress generated based on the payload and thrust force. So maximum stresses are generated are 13 megapascal. You can see the units here, megapascal, 13 megapascal. So where is the maximum stress occurring? Okay, so you can see maximum stress is occurring at the support side. That is payload, where we applied payload, right? So at that particular region, you can see the maximum stress occurring. Okay, and that too, the maximum stress is, even you can see that is a 13 megapascal. Okay, how we can say whether the model is safe or not? So the maximum stress is 13 megapascal. Okay, now we'll see the material is aluminum alloy. So what is the design point of the aluminum? Okay, now I'll go to the aluminum or aluminum alloy. Now you see what is the design point for the aluminum alloy. So yield strength or yield point is our design limit. So 280 megapascal. So aluminum alloy is having 280 megapascal. Now what is the equivalent stress? What is the maximum equivalent stress here? The maximum equivalent stress is 13 megapascal. but we can go up to 280 also, because the yield point is 280 megapascal. So we are in the safer region. You can see 13 megapascal is the only stress generated. Okay, now you can say it's a safer side. We are on the safer side. Okay, any doubts on this one? You can unmute and you can ask your doubts, because the first demonstration is done now. I'll be going to the second demonstration, model analysis on the same model. Meanwhile, if you have any doubts on this particular analysis, you can ask it. You can unmute yourself and you can ask it. Don't type in the chat box.
So
Yes, yes.
so you gave the displacement boundary condition, that it's the fixed support boundary
Right.
condition
Right,
at
right.
the landing gears.
Right, right.
But in real life, I don't think we'll be having any fixed support at that end, right? So won't it affect the
See,
results obtained?
yeah, we just showed you the static structural analysis. Okay, static structural analysis is done to identify the structural integrity when it is in the stable situation. Okay, so that means when it is in the that means what is the realistic deformation and realistic stress it will develop when it is in the flying mode. Okay, with the thrust force of 16 newtons on each and every motor, on having a payload of 12 kgs on the bottom. Okay, when this situation is happening in the reality, what could be the generated stress and what could be the generated deformation when it is in the flying mode? Okay, so if you have this kind of configuration with you, see, I just gave you the appropriate displacement to you. Why? Because if I don't give any fixed support or any boundary conditions, if I am not giving, the problem will not be solved. Why? Because Ku equal to F is the equation. If I don't give any displacements, defined displacements here, it won't show you the it won't show any values to you. Okay, it is just a representation to see what is the deformation and what is the stress generated when this particular the payload and the thrust force are acting on the object. In that situation, it is just a representation to replicate what could be the displacement and stress generated. Okay, I just gave you the fixed support. It is not a realistic case, that's true. But what I'm telling you, when you have the thrust force, see, when the object is in the rest position, do you think there will be any thrust? When the
No,
object
sir.
is in rest position, there won't be any thrust, right? Sorry,
Yeah.
thrust force, right? See, it is
Yes.
just a representation. Okay, when the model is having 60 newtons generated thrust on each and every motor, and the payload, if you see, that is a 118 newtons only. If you imagine, it will be in the in a flying condition only, right? With that given thrust and payload, it won't be on the ground. Okay, so I'm just showing you with respect to the the bottom the bottom landing positions. I'm just given the displacement by, because if I don't give, it won't be solved.
Yes, understood, sir.
Yeah, it is just
Thank
a representation to show you what is the stress and what is the maximum deformation occurs when this is in the flying mode. In the flying mode, it will have the thrust 60 newtons on each and every motor, and the payload is 20 kgs.
So one more doubt before I go.
நீ இந்த மாதிரி பேசாத, உனக்கு தான் ஓகே வண்டி, எனக்கு ஓகேனால தான் போட்டுருந்தேன்.
I'm sorry. Sir.
Yes. Go ahead.
So actually, there is another thing called analysis setting. You have opened it right now. So you have given 1 seconds. So won't the result be affected by that as well?
See, it is a static structural analysis. I'm not touching anything here in the analysis settings. It's a static structural analysis. And one more thing, I am on the the contact side. If you see, those are all linear contacts only. Okay, so what I'm saying, this static structural problem, what I showed you, it is a linear static structural problem. Okay, so in linear static structural problem, you don't need to worry about the analysis settings. If you have any non-linearity existing by means of the contact or by means of material or geometry, then only we generally disturb the analysis settings that time. Okay, right now it is a linear statics analysis. I did not touch any analysis settings. Okay, so why when you have to operate on the analysis settings means if you have large, I mean, if you have a nonlinear geometry, if you have a nonlinear material, okay, if you have nonlinear contacts. So just now, you know, it is all the things are bonded contacts. Those are linear contacts only. If you are having the frictional or rough or frictionless, these kind of contacts, if you are having class 3 contacts, if you are having, then the non-linearity contacts will occur. Because of that one, to handle those things, we have to stick to the iteration methods. Okay, direct methods won't be working there. So iteration methods I have to select. So iteration methods I can control using the analysis settings. There I can go to the, this auto stepping methods. I'll change it to on. Then I will give the number of substeps. So minimum number of substeps, maximum number of substeps I will define. That means iterative solution steps I will define. Okay, so these things will be active when you are solving non-linear structural problem. Am I clear?
Yes, sir. That's clear. Thank you.
Right now, what I showed you, that is only the linear static structural problem. That's why I did not operate anything on an analysis settings. If I am doing non-linear problem, then only I will define these substeps. Accordingly, I will identify. Okay. Yeah. Okay.
Hello?
Then yes.
Sir, I wanted to ask about the meshing. So I have faced the similar problem. The designer is different person, and I'm the analytic one. And the designer doesn't know anything about Ansys. So
Yes.
he doesn't know where the problematic body is, nor do I. Because
Yes.
so can we identify the problematic bodies in Ansys that are creating the problems for meshing?
Yes. See, since if you have the option here, see geometry. Let's say your friend gave you the geometry using some third-party CAD platform. Okay, so in that platform, there may be a chance of including extra surfaces, extra edges, extra penetrations, interpenetrations between the parts, right? So if you want to identify those things, you can open either space claim or discovery. Okay, so space claim is a good thing to go with. So I just show you. I won't do anything right now. I don't want to disturb anything. I am just telling you. I'm just answering you how we can do such things. How we can identify those things. Since you are not a CAD modeling person, but you can do the geometric cleanup. You can do. You may not do the preparation, but you can do the geometric cleanup by means of opening the space claim or discovery. Now you can see the platform here. So this is the space claim environment. Okay, here you can do such things. What you can do, you can repair the geometry. Okay, you can prepare the geometry. Okay, you can ask for interferences. That means in between the parts, is there any interferences you can identify? So now you see it's a very simple thing. Now you can see there are some interferences happening between the parts. Have you identified those things?
Yes, sir.
See, these are the regions having some interference problems. Okay, that is one thing. That is one thing. In the same way, repair option also, there is another option, repair option is there. So you can identify extra edges and duplicate faces here. I will go with the extra edges. See, there are 18 number of extra edges are there, and you have to sort it. Okay, how you will sort it? You can simply select this right click symbol. Okay, so whatever the possible extra edges fixing option, I mean, software will give you the automatic fixing option. Okay, so you just select it. It will fix automatically. So you can see fix the 18 problematic areas. In the same way, you can go to duplicates identification. There may be some duplicate features existing in your model. See, now you can see eight areas are there having duplication. Okay, so you can select it and you can remove those things. But what I am telling you, don't do it directly. Okay, it is just a one way of fixing your duplicates using the algorithm provided by the software. But the problem is, don't rely on the fixation based on the algorithm. Okay, sometimes it will give you the non-realistic fixation. Okay, always once you fix it, you have to ensure it has reached the proper connections. Okay, now you see, by selecting this one, it is not able to fix anything. Sometimes it may fix, sometimes it may not fix. Okay, but always ensure once it is fixed, you are always ensure it is having the proper geometries or not, proper connections or not. Okay, so what I'm telling you, ANSYS space claim or discovery is having these two options, prepare and repair. There you can identify those kind of geometry cleanups. You can perform geometry cleanup options by means of prepare and repair. Okay, yeah, that's it.
Thank you, sir.
Yeah. Okay, then,
So while
yes.
force,
Yes,
while
yes.
putting the force of 60 Newton on 6 surfaces, will it be equally divided and of
No,
10 Newton?
no. Each and every surface, on each and every surface, the 60 newtons will be generated. It's not a dividing thing. It won't divide.
Then totally it will be 360 Newton now.
Yes, definitely. Why? Because our thrust force should be more compared to the payload. Then only it will fly, isn't it?
Yes, sir. Okay. Thank you, sir.
I never flied anything. Okay, it's a basic thing. So more thrust force should be there so that we can have the flight. Okay, now coming to the second demonstration. So first demonstration is done. Now we saw stresses and deformations and we confirmed whether it is in safe region or not. Now coming to the model analysis. On the same model, we have to do the model analysis. So same settings, payload. Okay, so payload. Okay, now you see, coming to the loads and boundary conditions. Since it is a modal analysis, so in the modal analysis, you don't need to worry about giving the structural loads. Okay, so don't give any structural loads, whether it is a thrust load or payload. Don't give any structural load, only give the boundary condition, fixed support. Okay, and see what is the modal behavior or mode shapes of the hexacopter. Okay, so just remember what I'm telling. Don't give any structural loads. No structural loads we should give in the modal analysis. Okay, so what I will do, I will select the same geometry, that is B analysis I'll take. Okay, so what I will do, I will select a new analysis here. Okay, what I can do, I will select the modal analysis. Okay, I'll select the modal analysis. Okay, I will give the same thing. Okay, so engineering data, I will drag and drop it. I'll connect it. Geometry, I'll connect it. Okay, so model also I can connect it. Okay, it's not giving. Okay, so what I'm telling you, you can drag and drop the analysis and you can connect it the relevant information. And if you can remove also. Once you remove it, the connections will be broken, but still the data will be retained. Just a minute, it's freezing. Yeah. So this is one way of one way of doing the analysis. I think it's not deleting it. So what I'll just delete it. I'll delete the entire system, model system. Yeah. Okay, this is one way of doing. So what I'll do, model, I'll select it and I'll drag it and drop it. Okay, that is one way. Other way would be calling the analysis from the same mechanical environment. Okay, so this is the B system. Since I have selected the analysis system, I have disturbed the analysis system. That's why the solution has been disturbed. Okay, so you need to solve it again to see the results properly. Okay, but anyway, what I am showing you the modal analysis. So modal analysis, I'm inserting the modal analysis here in the environment. So modal analysis. Okay, so since I'm not using the static structural data, so I've just hidden it. Okay, now what I will do in the modal analysis, if you see, so modal analysis, it will take all the information in the previous steps. So it will take the geometry, it will take the materials data, it will take the connections, it will take the meshing data. Okay, only it will take what else we have to give. Now if you see the slide here, so we just need the same set of pre-processing stage. So modal analysis required, if you see the previous one, whatever the steps are there in the pre-processing of the static structural analysis. So I'm going to use the same steps here. in the modal analysis, except we should not give any structural loads, but we have to give the fixed support. Okay, since I have used the same data of the previous analysis, only what I will do the processing stages. So in the processing stages, I should not give any structural loads. I only give fixed support, and I will see the results. What are the results? Natural frequency, mode shapes. Okay, those two things I'll show you. Okay, so what we have to give? We have to give only the boundary condition, that to displacement boundary condition only I have to give. So fixed support. Again, the two surfaces I will select. So two faces I will select here. So one is this surface and another is this surface, and I'll apply it. Okay, so those are the two surfaces, that is the fixed support, and we are not giving any type of loads here. Why? Because that is the requirement of the modal analysis. In the modal analysis, if you see the equation of the modal analysis, there you won't be watching any, the inclusion of force you won't be watching there. So that's why we are not giving any structural data here. The structural load we are not giving. Okay, now what I will do, I will identify what are the number of modes I want. Okay, so by default it is having 6 number of modes. Okay, you can increase it to 20 also. Okay, so 20 number of mode shapes I am requesting. Okay, then I will solve it. Again, same number of elements and nodes I am having. So 1 lakh number of elements are there, 3 lakh number of nodes are there, using the 4 number of cores. 4 number of cores I'm using, and I'm solving for the modal analysis. Hopefully you are aware of the modal analysis. What is the objective of modal analysis? Modal analysis is done to identify the natural frequencies. Okay, once you identify the natural frequencies, we will take care such that the external force will not have that natural frequency of excitation. Okay, so modal analysis is done to identify the natural frequencies and the corresponding mode shapes. Okay, so once the natural frequencies are identified, we will ensure the excitation frequencies should not match with the natural frequencies of your model. Okay, we know already what will happen. If the excitation frequency matches with the natural frequency, then your resonance will happen, and that will lead to the catastrophic failures of your model. Okay, now 20 modes I have asked to extract. So now you can see those 20 mode frequencies. So you can see these are the frequencies of your model. So starting with 11 hedges to 20th mode is having 112 hedges. So these are the frequencies, natural frequencies of your mode. Okay, so what I'll do, I'll extract all those mode shapes here. So I'll select all those things, and I will right click it and create the mode shapes. Now you can see all the mode shapes corresponding to each and every frequency. You can see it here. So what I will do, I will evaluate all the results. So for each and every frequency, what is the mode shape we will see. So first mode shape is corresponding to first mode shape is this is the first mode shape, and we know what is the frequency of the mode shape. So frequency of the mode shape is 11.153 hedges, and that is the 11.153 hedges. So and this is the deformation of the first mode shape. See, this is one mode shape of the first frequency, first natural frequency. In the same way, I'll select the fifth one. You can see only the propellers are having the mode shapes. Ninth one I'll see. Again, a different set of propellers are having the mode shapes. This is another mode shape. So objective of the modal analysis is to identify the natural frequencies. Now you can see in the 19th mode shape, you can see the arms of the motors. They are having the deformations. Okay, so these kind of mode shapes, they are corresponding to the frequencies, natural frequencies. Okay, so we should avoid these frequencies while having the excitations. Okay, so excitation means repeated load. Let's say the motor is running with some RPM. Okay, so RPM, the frequency of that motor RPM should not match with any of the frequencies shown here. Okay, so that is a criteria we need to take care. So that is about the model analysis. Any questions are there? So these are the model analysis mode shapes and corresponding the natural frequencies. Okay, so these are the two demonstrations we planned for you. So the first demonstration is on static structural analysis of the hexacopter, and second is the model analysis. Okay, so with this, the demonstration side is done. Then I will take some 10 minutes to showcase you the best practices generally followed in the industry. So best practice. Yes, yes. Yeah, just I'll take 10 minutes to cover these practices. Okay. So best practices, if you see, there are a set of best practices. So the first one is the mesh convergence. So mesh convergence. Right now we have seen we have included the 4 mm mesh size in our model. Okay. So whether the solution is correct with respect to the generated mesh. Okay. So that can be taken care by using the mesh convergence. So by increasing the number of element size. Okay, body element size, you try to reduce it 2 mm, 4 mm, 6 mm, 8 mm, 10 mm. Okay, you just do this, do the analysis with respect to the different element size and plot the stresses. Okay, so if the stress is having the horizontal line, then you can say the mesh is convergent. The mesh convergence study has been reached. Okay, so what you have to do, you have to vary the number of elements and you do the analysis again. Okay, so the results should be independent of the mesh. Okay, that is the main aspect of doing this mesh convergence study. So mesh convergence study we have to perform. Okay, so that the results, whatever the results are there, they should not depend on the type of mesh what you're using. Okay, that is the mesh convergence study we do. Okay, then coming to the mesh quality. So mesh quality, there are different metrics are there for the mesh. Okay, so there are different mesh qualities. I just show that one here. So mesh metrics. So if you go to the mesh, then here in the quality, so there are mesh metrics options is set to none. So if you see what are the mesh metrics we are having, so element quality, aspect ratio, so there are different mesh matrices are there. So you just check the element quality. Okay, now you see the element quality. Okay, in another way I will show you. So element quality, now you see the element quality, whatever the mesh generated here, if you see the elements, the element quality of all those elements, so it is varying from 0.016 to 0.09. So ultimately, to have a good result or to have a better analysis, the element quality should be lying between 0.2 to 1. Okay, since the elements are falling in 0.016, okay, so you have to update the mesh such that the element quality of all the elements should fall within 0.2 to 0.99. Okay, just remember this one, at least element quality should be falling between 0.2 to 0.99. Okay, right now the mesh generated is having 0.016. That means the element quality of the few of the elements, they are having the element quality is not within the limits. Okay, so you need to update the mesh accordingly. So that is about the element mesh quality. So ensure that your mesh metrics and quality should lie with respect to the limits mentioned. So element quality, if you are sticking with, the element quality should be falling between 0.2 to 0.2 to 1. Then again submodeling. Okay, so if you have a complex the complex geometry if you are having, okay, so sometimes if you, let's say, some welded region is there, okay, or otherwise some proximity is there between the parts. Okay, so those kind of parts, what you can do, you can separately do the analysis by creating the submodeling sections. Okay, so let's say if you see the figure, there is some particular area. So if I want to see the results on that particular submodel, so you can select that areas, you can select the submodeling sections. Okay, you can separate the part on that particular focused area, then you can do the analysis again. That is about the submodel. Then other meshing best practices are there. So meshing best practices. Just a minute. So always try to have the hexahedral mesh. Okay, since hexahedral mesh requires less elements than tetrahedral. Okay, so this is the one meshing best practices. So since if you see the previous mesh I showed you, it is having mix of 3 different type of elements. Tetrahedral elements are there, hexahedral elements are there, wedge elements are there. So what it is saying, if you have hexahedral elements entirely in your model, that will be a good thing. Why? Because more number of tetrahedral elements, hexahedral elements will take less elements compared to the tetrahedral elements. Okay, to capture a particular area, if you can use hexahedral elements, that will take less number compared to the tetrahedral mesh. Okay, next again, sweepable bodies. Since I think I should not spend much time on this. Why? Because all these things you can understand if I show you the examples corresponding. So each and every step I have to show you the corresponding example, then only you can understand. Okay, so quickly I'll cover these things. Okay, so if you have a sweepable bodies, sweep mesh will be the best option. Okay, so sweepable bodies if you are having, then you have to go to the local meshing of sweep mesh. Okay, so that's the one thing. And mesh quality, I told you already, mesh quality. So mesh quality, if it is a element quality, then it should be within 0.2 to 0.99. Okay, let's say if you are having less than 0.2, what will have, it will show some impacts on your analysis results. Okay, so it has a huge impact on results accuracy, and bad mesh can lead to wrong results. Okay, so bad mesh means what? Right now I just showed you, we have elements quality, few elements are having the element quality of less than 0.2. So because of that one, it may be some wrong results possible. Okay, so by default Ansys will do quadratic elements. See, I told you. So by default quadratic elements will be generated. That is what I showed you. And from your system, if you are having a basic system with you, always try to do the linear meshing instead of quadratic meshing. Okay, that will reduce the number of nodes existing, so that you can easily solve the problem with your limited hardware. Okay, likewise, then type of analysis. Okay, then always ensure what type of analysis you are doing, whether you are doing static structural analysis or quasi-static or creep analysis you are doing, a dynamic analysis if you are doing. Okay, otherwise, if you want to do the drop test, impact test, generally you people have to do the drop test, impact test, bird strike test. Okay, so these kind of tests, if you are interested, then you have to stick with the explicit method analysis, that is LS-DYNA. So you have to use LS-DYNA, not the static structural or modal analysis. Okay, you have to do the LS-DYNA. You have to use the LS-DYNA, or otherwise explicit analysis you have to do. Okay, so explicit analysis means, again, if you see, so in the workbench, if you see, you can see the option of selecting the LS-DYNA or explicit dynamics. Okay, so explicit dynamics or LS-DYNA you have to call. So accordingly you can do. So if you are doing crash test, drop test, all those things, then you have to stick with this LS-DYNA. So that is a chart here, it is shown. So based on the time frame, if it is a less duration, long duration problem, that means 1 second, 10 second, 1 year. So if the problem duration is this much, then you can use the implicit methods. If it is a short duration problem like drop test, crash test, and balastics, okay, this kind of impact studies, then you can go for the explicit method, that is LS-DYNA solver. Then material modeling. Just now I showed you the isotropic elastic material, because I know about the aluminum alloy, that is a isotropic material, and it is a linearly elastic material. Okay, otherwise if you are having composite, it may be it could be orthotropic material. Okay, so accordingly you can select the corresponding material. So for elastic material you can select plasticity, creep, viscoelastic, and additive manufacturing materials also we just showed you, titanium 6 TiAlv4. Okay, so those kind of materials you can wisely select according to the needs of your model. Okay, then then this is again another adaptive convergence. So it is similar to the mesh convergence. Okay, but right now I can't spend much time here. So okay, this is one way of doing the convergence studies, mesh convergence studies we can do. So instead of remeshing every time, okay, what you can do this adaptive convergence in the post processing side. Okay, so once you have the equivalent stress, there you can insert the the convergence criteria by simply right clicking on that particular stress component. Okay, so stress component, you select the just to show it in the here itself. So let's say you have the stress with you. So in the stress, equivalent stress, right click, insert. There you will have the convergence. Okay, you can set the convergence limits here. Okay, so with setting these limits, you just run this step, you will get the adaptive convergence. Okay, whether it is depending on I mean different. You can see it here from the figure. So from the figure, you can see different number of elements are there. Okay, so by having the variation of 20% of the equivalent stress, you can have the adaptive convergence. So what it says, it helps users discover mesh independent solutions, so the results don't change noticeably with further mesh refinements. Okay, so the results, let's say 20% if I keep, so that means the results will not vary more than 20%. Okay, so based on that limit, it will do the automatic or adaptive convergence studies. Then again, parametric studies. So initial slides I told you, this is the last cell of the analysis. Okay, so if you define the input parameters and output parameters, then you can have the option of doing the parametric study. Okay, so input, I'll just show you, this is the last one. So let's say if you want to change the payload, okay, what you can do? So payload, we just kept only 118 newtons. Okay, so if I want to change the payload, if I want to give a multiple value of that magnitude, let's say 2 into 118 or 3 into 118 or 20 kgs, 30 kgs or 60 kgs. Okay, so what I can do, I can define the parameter here. Simply I select the parameter P. Okay, so this is the input parameter. So they can ultimately what you want to see. So if I want to see the equivalent stress, okay, so equivalent stress maximum value if I want to see. So what I will do, what I did here, so payload I gave the input parameter. Okay, then again equivalent stress I gave the output parameter. Okay, I just want to see the variation of equivalent stress with respect to the payload. Okay, so accordingly I gave the input parameter and output parameter. So accordingly I'll run the study. Okay, that is a parametric study. So input parameter, you can give material properties, mesh, geometry, loads, point masses. So these are the input parameters, and output parameters you can identify stress, strain, deformations, and you can do the parametric study. So with a single click, you can do the parametric study. Okay, once you set the entire analysis, you define input parameters and output parameters, and you conduct the studies. Okay, accordingly you can see the variation of the input parameter with respect to the output parameter. Okay, so that is about from my side. Okay, so if you have any queries, we can discuss here now.
Yeah, please feel free to unmute yourself, and if you have any further questions. Actually, there was one question, Shyam, which said, if we can probably mention 3 or 4 common mistakes that people make when simulating multi-rotor drones, and if there is any way that they could avoid while simulating this. Any 3, 4 critical pointers, common mistakes that people make.
Common mistakes will be already a few people they just mentioned, right? So mesh, while generating the mesh, they have some issues, right? So what they can do, once you import the model or once you create the model, always do the geometry cleanup using the space climb or discovery. Okay, I just showed you already. So repair and prepare steps are there. So using those 2 things, we have multiple options there in those 2 steps. Okay, so accordingly we can identify duplicate faces. Okay, so geometry cleanup you need to do. That's the first thing. And second thing is generating the mesh. And while generating the mesh, always ensure mesh quality should be within the limits. Like I told you, element quality should be 0.22.
0.2 to 1. The element quality of all the elements should be falling within 0.2 to 1. If it is not falling, then you remesh it. Okay, that is the second thing. So, and the same way, number of elements. Okay, so whether you want to do the linear or quadratic elements, that also we need to be careful. And mesh convergence study also you need to perform. Okay, so first thing is geometry cleanup, and second thing is mesh convergence study. And those are the two things. Those are the two things initially we can remember. Yeah. And based on the type of analysis, okay, whether it is a static analysis or a dynamic analysis or explicit analysis, okay, the objective should be clear. So while performing, while having their object performing, so what could be the hurdles they can have? Accordingly, they have to identify the type of analysis. If there is any problem of hitting with the walls or hitting on the ground, or maybe crashing with the bird crash kind of things, okay, if those things are there, short duration events are there, then you have to do the explicit analysis. Otherwise, if you are having the confined space testing, like outdoor indoor testings, if you are having, so the bird strikes, so those things are not required. If the height is not much, if you are having confined space less, 2 or 3 meters height, if your objective for having the hexacopter to fly, then we don't need to perform the drop test also, because 2 meters I don't think we need to perform the drop test. Can I simulate propeller induced oscillations affecting mounted electronics using harmonic response or transient structural analysis? Propeller induced oscillations. Yes, that can be done, but you need to include all the data, all the details clearly. Like you have to keep the kinematics of the electronics part mounted, or maybe the camera gimbals what you are having. Okay, so you can do such things, because simulation, all the kinds of simulations you can perform using your Ansys. I just showed you the categories, right? A single slide, there is a category: static, dynamic, creep problems based on the time frame. Okay, one slide I showed you, right? So we have all the options. We have all the ways to do the such analysis. The non-realistic simulations also we can do. Non-realistic things. You simply imagine the type of criteria. Accordingly, you can simulate the things. Let's say generally drones, right? So drones, generally nobody will do the bullet impact analysis. If you imagine, you can perform it. So there is no limitation on your thinking. We can do that. Propeller induced oscillations affecting the mounted electronics. Yes, that can be done. Dynamic analysis. Yes, it is done. It can be done. Sumit, sorry.
Yeah, dear participants, I've actually shared a feedback form link in the chat window. Please see to that, if we can just fill up that feedback form.
Yeah, if you guys need any dedicated things like static structural model analysis, okay, so I just covered you. If you are performing any more like dynamic analysis, if you are performing, or explicit analysis if you are performing, okay, that can't be taught on these particular sessions here. Okay, so those things you need to approach our support system. Okay, you can write to our mail ID, support@cadfem.in, if you have some queries or basic queries also. We'll try to address it accordingly. Okay, that's one way. And Ansys innovation courses also you should need to utilize wisely. Just have a look on the Ansys innovation courses. It is having plenty of courses according to the student competitions. Okay, just have a look on Ansys innovation courses.
Yeah, I will share the link in the chat window as well.
Yeah. And Venkatji, can we? Is there any way we can share these information to them? That means particularly this model I can share with them if they want.
Yes. If you can just share it to me, I will send it out to Suman and Dinesh. I mean, the SA India team.
Yeah, sure.
Then we could probably share it across with the participants. We can share the model and all of that with the participants. It'll be excellent. Yeah.
Topology optimization session that's not covered, that's not planned actually. So, but we can plan it, but I don't know how we can we can do those things right now.
We'll discuss with the SAE team and I'll come back to you guys on that.
Yes. If you have a bunch of students who are interested in the topology optimization, put a request to the the organizers, and we can have that thing. We can retrieve how many modes from the model simulation. Till what mode are we supposed to consider first? Yeah, that's a good thing actually. So that's a good question, Tyagarajan. So there is a participation factor. Mode participation factor is one thing is there, because we don't have a time. I could not cover it actually. So the number of modes to be considered, it depends on the mode participation factor. Okay, so you just search once in the Ansys help documents also. So when we can start, how many number of modes we can consider for having for the proper capturing of the data. So that is based on the mode participation factor. So if you select, let's say I've selected I just showed you the 20 mode shapes, right? So for the 20 mode shapes, you have to check the mode participation factor. If the mode participation factor is less than 0.9, that means up to 0.9, if you are having the mode participation factor, that is sufficient. Okay, so the number of mode shapes, the number of modes or frequencies, that will be depending on the mode participation factor. Always ensure it should be crossing more than 0.8 or 0.9. Up to that, we can take that many number of mode shapes. Just remember, mode participation factor is the criteria. For CFD also, CFD, the sessions will be covered in the next weekend.
Yeah, I've shared the link and I've also shared the invite in the.
It will be on 10th May. Yes. Yes. Generally, generally, no, it is not like that actually. Low frequencies. One way I can say that is correct, but in another way, we have to consider all the frequencies also. See, the criteria is whatever the excitation, external excitation is coming on your system, it should not match with any of the natural frequencies you are capturing. Ultimately, that is a hectic thing only, but we can stick with at least 4 or 6 number of initial mode shapes. 6 will be a good number. 6 will be a good number. We don't need to worry with considering all the mode shapes. Okay, one way it is correct, one way it is not correct. Sir, should we include gravity force in the model? No. It's see, simply see the equation actually. So equation is m into a plus k into u equal to 0. See, just now I said the equation m into a plus k into u equal to 0. Okay, in that equation 0, there should be a force generally, but in the model analysis, that is the equation. There is no inclusion of force. So that's why even the gravity force also we are not including. Gravity force is nothing but the payload. The kg is multiplied by the gravity. So payload force we are not including. Yeah, and Venkat sir, he just shared few innovation courses relevant to you.
There's one more question, Shyam, that has come.
It's a good thing. That is what we are doing the model analysis. The drone, if you select the 10 mode shapes, okay, 10 different frequencies will be there, right? So you select the motor frequency such that it should not match with any of the natural frequencies of your drone. Yes, it is okay. It is okay.
Any other questions, Shyam? That's coming.
No questions are there other than this. Hopefully, we have answered all the things. Less means, what is that? Less means my drone frame is flexible. No, I didn't understand. See, we generally identify the model analysis. Model analysis for your model without the payload, right? Yes. Yeah, you can speak.
Sir, so I wanted to ask if my model frequency of my drone is less than the more natural frequency of my motor, then the
Yes.
drone frame is flexible. That means
Yes.
it will vibrate more when the motor is
No.
attached.
No. It is not like that. See, the frame. See, no need to worry about the single part. See, frame means are you referring to the entire geometry along with the frame or the only simply frame?
Only frame.
No. We generally do the model analysis on the entire system, not on the frame. No need to worry. Because
Okay.
if you see the frame, it will be connected to other parts as well, right?
Yes, sir.
The frame will be connected to other parts as well. So that's why we don't need to worry about the single part. We can worry about the entire part, entire assembly. Only we will do the model analysis, and those natural frequency of the entire model only we will be comparing with the natural frequencies of the external sources.
Okay, sir.
Yeah.
Thank you, sir.
Yes. Okay then, Venkatji.
Yeah, I think that's yeah. Right, Dinesh sir, are you
Yes,
there?
sir. Yes, sir. Thank you,
Yes.
Mr. Sham. Thank you for the wonderful, seminar. Thank you so much.
Thank you.
Right, sir. I've actually shared in the feedback link. What I'll do is that after the recording is done, I'll share the access to the recording as well, and I'll also share the workshop files that Shyam was talking about for this session
Yes,
to
sir. Yes.
and the entire team there. Yeah.
Yes, sir. Noted, sir. Yeah, we'll do that.
Right.
Thank you so much. Yeah.
Thank you so much. Thank you everyone to be part of this session. Thank you, Shyam.
Thank
once
you.
again.
Thank you.
Bye-bye. I'm
Thank you,
closing this
Suman.
session officially. I'm closing this session officially.
Yeah. Yes, sir. Thank you, guys. All the best. Bye bye.